Recording in progress.
As chair of IEEE CSS RES Joint Chapter, I take great pride in welcoming all the attendees of the 2021 International Conference on Mechatronics, Robotics, and System Engineering, especially for our honorable and distinguished keynote speakers, Professor J. Katupitia from University of New South Wales, and Professor Maki Habib from the American University in Cairo, and Dr. Nico Saputro as the General Chair and all the committee as well. We are delighted to have you among us. On behalf of IEEE and committee, we would like to extend our warmest welcome and good wishes. Welcome to the IEEE publication through morse 2021. A non-for-profit organization, Institute of Electrical and Electronics Engineer, is the world's largest technical professional organization dedicated to advancing technological innovation and excellence for the benefit of humanity. As the largest publisher, we have to keep the quality of the accepted papers before the submission to the IEEE Explore. As soon as this conference is over, we sincerely request and expect all participants to immediately re-examine and revise their papers, both based on reviewer comments in the letter of acceptance and audience comments in today's parallel session. Before submitting to IEEE Explore, we, from the IEEE CSS RES Joint Chapter team, will review the compiled papers one by one. If the authors do not revise it properly, we will review it again and return it to the committee. The committee will return it to the authors and vice versa. Of course, this process will increase the time for your paper to be published. If we do the review process again, there will be most likely additional comments. If you don't want to get additional comments, please immediately revise them carefully, accurately, and correctly. Generally, the eye-catching errors are overall format, image quality, and technical problems can also be found in English quality, the structure of the paper, such as numerical results in the abstract and conclusion, literature supports from currently published paper from reputable journal, clarity and regularity of writing methods, and quality of discussion. I hope that the things I have mentioned above will be re-examined more carefully by both authors and committee. If we are able to follow all the instructions, usually the paper will be published less than 1 month after the submission to the IEEE Explore. Most recently, in the last August, papers from Universitas Prima Indonesia were published within 10 days after the submission. Once again, thank you for the hard work of the committee so far, and especially the review process after the conference. Chair of IEEE Indonesia CSS RES Joint Chapter, Arjon Turnip, PhD.
And now we would like as well to invite Vice Chair of IEEE Indonesia section to give his remarks. Let us welcome Professor Gamantio Hendra Toro.
Thank you. Dear distinguished guests, colleagues, researchers, professionals, students, ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Prosperous and warm greetings to all of you. First of all, I would like to thank the chair of the committee for the 2021 International Conference on Mechatronics, Robotics, and System Engineering, morse 2021, for inviting the chair of IEEE Indonesia section to give a few words at the opening of this conference. On this occasion, I am speaking here on behalf of the chair of the IEEE Indonesia, as he could not attend this conference today due to other commitments. the honorable speakers, Professor J. Katupitia and Professor Maki Habib, the Honorable Dean of the Faculty of Industrial Technology of Parayangan Catholic University as the host of the conference, the Chair of IEEE Indonesia Control System Society and Robotics and Automation Society Joint Chapter, the General Chair of Morse 2021, as well as all participants. On behalf of the Chair of the IEEE Indonesia section, I am happy to welcome you to Morse 2021. I would like also to thank everyone who has made this conference happen today. First of all, the Department of Mechatronics Engineering, the Faculty of Industrial Technology of Catholic University, who have been very kind to host this conference. Also to the IEEE Indonesia Control System Society, Robotics and Automation Society Joint Chapter, who serves as the technical co-sponsor for this conference. And of course, the speakers and moderators involved. While the scope of this conference might fall into the fields of control systems, robotics, and automation, but as a telecommunication engineering, I myself feel very proud to have this opportunity to speak here because the acronym of the conference is MORSE, who was and I still is one of the greatest inventors in the field of telecommunications. A conference is a medium in which researchers disseminate their research works orally and obtain direct feedback from the audience. Such a process will hopefully improve the research works, which will later contribute to the enrichment of scientific knowledge in the fields of electrical engineering, and at the end of the day, will benefit the humanity. This conference shall aim to enrich knowledge about the latest issues, opinions, bright ideas from researchers and academics. New innovations and in technology for a better future are emerging, including and especially in the fields of control systems, robotics, and automation. Collaboration between universities, industry, and government is important in creating jobs and developing civilization. I hope that Morse 2021 can encourage discussion and hope to inspire participants from a variety of teams to start collaboration within and across disciplines for the advancement of science. Sessions may also show important scientific progress and highlight the impact on science and technology. I hope all of you will have a productive and enjoyable time at this very special conference. Honorable guests, speakers, ladies and gentlemen, IEEE Indonesia, as a regional organizational unit of IEEE, serving the IEEE members in Indonesia, was founded in 1988, and in its development over the past 33 years, IEEE Indonesia has contributed significantly in various activities that encourage the role of science and technology for humanity in Indonesia. IEEE Indonesia, together with volunteers, members, and all stakeholders, have produced various activities by supporting of more than 20,000 IEEE conference publications and more than 260 IEEE journal publications by Indonesian authors since 1988. Despite these numbers, we still need to encourage the growth of scientific publications from Indonesian authors in high-quality IEEE journals. IEEE Indonesia has also sponsored and support more than 50 high-quality conferences each year. The results of the quality conference publications are published in the IEEE Explore digital library, indexed by Scopus, Web of Science, and other major databases, which have more than 5 million publications and more than 12 million downloads each month. As we all know, IEEE always maintains high-quality publications as part of the intellectual culture. IEEE Indonesia also holds more than 40 professional, technical, non-technical, and administrative activities each year for all its members. Currently, we have more than 2,600 members and more than 50 senior members consisting of professionals, industries, academia, and government. Currently, IEEE Indonesia also supports the development of 25 technical society chapters and joint chapters, which are each a forum for technical activities for members in Indonesia. IEEE Indonesia has also supported the development of 24 university student branches and 9 IEEE student branch chapters, which become a forum for technical and social activities that provide the best experience for Indonesian students and graduate student members. In addition, we also have a non-technical affinity group consisting of young professionals and women in engineering and one IEEE site on e-health and telemedicine interest group. This year, IEEE Indonesia has also initiated cooperation with the Directorate General of Higher Education of Indonesia in order to synchronize and support IEEE activities with the Indonesian Ministry of Education and Culture program, especially for the Free to Learn Free Campus program. IEEE Indonesia is also exploring cooperation with Indonesian industry in various activities. In addition, IEEE Indonesia is also actively involved in providing input in the preparation of related government regulations as well as other activities. Our most recent effort is to launch the IEEE Innovation Nation program in Indonesia with the hope that we could help support the development of new innovative startups by local people in Indonesia. I would like to encourage any of you who are not yet an IEEE member to join us and become a member to experience all of these opportunities, to work together and collaborate in these various activities. Finally, I realized that putting together a conference like Morse 2021 is not an easy task. We are grateful to all parties who work together to help build this very interesting conference program. We hope that Morse 2021 can be a fruitful and memorable event. Stay active, stay healthy. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Professor Hendran Toro. Ladies and gentlemen, we would like to request our last speaker to give his remarks and to officially open the Morse 2021 conference today. Please join me to welcome Dean of Industrial Technology Faculty of Parahyangan Catholic University, Dr. Teddy Yogasara.
Thank you. Good morning, good afternoon, good evening, whichever time it is where you are. The Honorable Head of Department of Mechatronics Engineering, Parahyangan Catholic University, the Honorable Keynote Speakers and Chair of the Organizing Committee, the Honorable Chair of IEEE Indonesia and Chair of CSS RAS Joint Chapter Indonesia, esteemed presenters, students, and all enthusiastic participants and guests. It is my pleasure to welcome you to the second International Conference on Mechatronics, Robotics, and System Engineering, or MORS 2021. And despite the COVID-19 pandemic that prevents us from meeting physically, we all are grateful for our health and for being able to participate in this important event. The Department of Mechatronics Engineering, Parahyangan Catholic University, or UNPAR, has put together an excellent international forum for academics, researchers, industrial practitioners, and students to embrace and share their latest research, techniques, and advanced development in the fields of mechatronics, robotics, and systems engineering. This event also serves as a useful bridge between academics and industries, and as a means of creating beneficial networks for the development of mechatronics and electrical engineering world. I feel exceptionally happy and grateful as this year Department of Mechatronics Engineering managed to bring this conference to the international level for the second time. And it is the first time for the conference to be held using online platform. Previously, in 2019, MORS took place successfully in Bali, Indonesia. This event in the future hopefully would be an iconic program of the Department of Mechatronics Engineering UNPAR. I feel very proud and pleased that our departments in the Faculty of Industrial Technology UNPAR have been consistently organizing and holding quality programs that promote acknowledgement and recognition to our faculty and university, both nationally and globally. Relating to that, ladies and gentlemen, please let me take this opportunity to introduce our faculty. Our Faculty of Industrial Technology was established in 1993 with two departments, Industrial Engineering and Chemical Engineering. Currently, these two departments have been accredited by the National Board for Accreditation with rank Excellent, which is the highest level possible, meaning that we provide the best quality in higher educational services. In addition, our chemical engineering program has also been accredited internationally by IAB, or Indonesian Accreditation Board for Engineering Education. In 2015, we proudly introduced the third undergraduate program in our faculty, which is Mechatronics Engineering. This youngest program has also been accredited, achieving very good rank. Currently, our faculty consists of around 1,500 students and more than 60 permanent teaching staff and researchers. Our faculty also offers master programs in industrial engineering and chemical engineering. Ladies and gentlemen, with regard to the vision of UNPAR, I hope that the development of the use of knowledge in mechatronics, robotics, and system engineering can also be focused on the utilization of Indonesia's natural resources and various local potentials, and subsequently bring them and introduce them to the international level. Moreover, I believe that this conference could be a means for facilitating and equipping us in facing the era of Industry 4.0, which is characterized by Internet of Things and cyber-physical systems. The advancement of mechatronics technology and knowledge needs to be directed towards intelligent production, cloud computing, big data, advanced robotics, artificial intelligence, and nanotechnology. With the advent of the fourth industrial revolution, many of humans' roles and jobs will be replaced by robots and artificial intelligence. Therefore, it is essential to prepare future human resources who have unique and superior skills, as well as spirits of transformation and innovation. Distinguished guests and participants, putting together morse 2021 is a team effort, and I first would like to thank the head of Department of Mechatronics Engineering UNPAR, the chair, and the organizing committee who have worked very hard for the success of this year's morse. Secondly, I would like to express my sincere gratitude to the keynote speakers, Professor J. Katupitia and Professor Meki Habib, who are willing to share their expertise and time for this conference. Special thanks also goes to IEEE Indonesia and CSS RAS Joint Chapter Indonesia for their significant support. Finally, I would like to once again thank all participants for taking part in morse 2021 and making this great event possible. I wish you all a successful conference with fruitful discussion and inspiring findings. The honorable participants and guests, by giving thanks to God, I declare that the 2021 International Conference on Mechatronics, Robotics, and System Engineering is officially open. Thank you.
As this conference has been officially opened, we would like to give our appreciation to the speakers and invited guests who have given their remarks at this opening ceremony. Before we proceed to the next sessions, let us take picture together. Please activate your camera, and one of the committee will guide us in this photo session.
Okay, ladies and gentlemen, we will take a picture together. We start with the first screen. We will have, I think, three screens. So, first for the first, sorry, we have 4 screens. We will take the first screen. I will count to 3. 1, 2, 3. Then the next, the second screen, I will count again. 1, 2, 3. The third screen. Okay, let's start to count. 1, 2, 3. And the final screen. 1, 2, 3. Okay, we done. Thank you very much.
Dear all conference participants, it is time for us to join the first keynote about autonomous agriculture vehicles and active implements for high precision operations. Our first plenary talk will be delivered by Professor J. Katupitia from University of New South Wales. Dr. Jonathan Chandra will become the moderator of the talk. Without further ado, Dr. Chandra, please guide us for the first keynote.
Good afternoon from the west of Indonesia, distinguished guests and participants. Welcome to the first keynote session of morse 2021 virtual conference. My name is Jonathan Chandra, and I will be serving as the moderator for the first keynote session brought by Professor J. Katupitia. Is Professor J here?
Yes, I'm here.
Okay. You'll be hearing a presentation from Professor J. Katupitia on this very timely subject. But before we get started, I'll read a short biography of Professor J. Katupitia. Professor J. Katupitia graduated from the University of Peradeniya, Sri Lanka, specializing in production engineering, and later completed a PhD in mechanical engineering, specializing in robotics. He later joined the University of New South Wales in Sydney, Australia, and currently a member of the academic staff of the School of Mechanical and Manufacturing Engineering. He was also the deputy head of the School of Mechanical and Manufacturing Engineering and did pioneering work to establish the mechatronic engineering program at the New South Wales University and was the head of mechatronic engineering program for more than 10 years. Now, he's currently managing director of Tronfield Robotics and Trontech Autonomous Systems, which is two sister companies developing an autonomous agricultural vehicles. Not to forget, his research expertise is in the areas of autonomous field vehicles and space robotics. Now, moving along to our session, please welcome Professor J. Katupitia, who will be speaking to us on autonomous agricultural vehicles and active implements for high precision operations. Not to forget, you may also ask any question related to the topics using the Zoom chat features. Okay, Professor, the stage is yours.
Thank you, Jonathan, for the introduction. Do you hear me clearly?
Yeah, crystal.
Can I share my screen?
Yes.
Okay, thank you. Do you see my screen?
Yeah.
Okay, right. First of all, I'm really very thankful to the organizing committee of morse conference and inviting me to do this presentation. So as I agreed, the title is Autonomous Agricultural Vehicles and Active Implements for High Precision Operation. Basically, my aim today is to tell you the kind of work we have done. This will be mostly on engineering side of work. We've done quite a lot of theoretical developments and they are all nicely written out there. And I will also show you where you can find the research work that we did in this area. But mostly I'd like to tell you the important aspects of autonomous agricultural vehicles, especially why we need high precision and why we need active implements. So basically what I'm saying by active implements is that implements themselves have some form of control systems operating while the implement is working out in the field. Normally in agricultural operations, when a tractor or some other prime mover is pulling an agricultural implement, the implement simply drags behind it without taking any active controls to do some improvements of its work. So that is what I mean by active implements. So you will see that the implements that I will be showing has some active components in them. Okay, so let me change the slides. First of all, my affiliation. So I am an associate professor at the School of Mechanical and Manufacturing Engineering, University of New South Wales, Sydney, Australia. I especially put this Sydney photo. Sometimes people get confused about New South Wales as a place in United Kingdom. I am right now actually in Australia. So this University of New South Wales is a place in Australia. It's one of the great universities in Sydney. We also have this website if you need to see what we do. This is mostly related to the Thorntech Autonomous Systems and Thornfield Robotics companies, but the work is actually shared. So my background, I have developed high precision autonomous agricultural machines over a period of more than 10 years. And the technology is actually commercialized, so it has got the United States patents as well as Australian patents. And we have also developed high precision autonomous bulldozers for Komatsu with some participation, collaboration with them. We have also developed high precision road construction machines to compact the ground by the sides of newly laid concrete slabs of highways. So these are all field vehicles, as you can see. So we are not working in the urban transportation or anything like that. Largely, the heavy vehicles operating in the field is my area of specialization. So autonomous agricultural machines, I'm going to describe this in a bit of detail, and that's why I have put all these steps here. So the example system that I'm going to present, which is, it does not have to be this system, it can be any system. So it is called a broadacre seeding system. By broadacre, what I mean is large fields growing crops such as wheat, barley, canola, sometimes grass for Japanese cattle market. So these kind of large areas growing crops are called broadacre farming. So in Australia, we have fields that are 10,000, 15,000 hectares large, and this is quite common in some parts of United States and Canada, and also it is becoming common in South America. There's not a great deal of land left in Europe, therefore the farm sizes may not be this big. I'm not 100% sure. So that is what broadacre farming means, and seeding is planting the seeds, and it does not have to be seeding. You can do plowing, you can do fertilizing, you can do weeding, all kinds of operations can be done, but in this example, I'm using seeding. So the basic premise behind the development of these machines is split the machine into two. One is a pilot vehicle, the other one is the implement. So the pilot vehicles are generally small in our design. In normal situations, the pilot vehicle or the vehicle in front is capable of pulling the entire implement regardless of what kind of work it does. Even when it engages the ground, the forces rise rapidly and the prime mover in front is capable of pulling this implement. But in our case, the pilot vehicles are very small, but they are supposed to pull implements that they cannot really pull. So how do we do that? So that is why this says that the implement has its own power unit. So this one here says implement has its own power unit. So implement is to some extent powered. So the implement driving power comes from the implement itself. And the pilot vehicle is fully instrumented. And we have these two vehicles controlled differently. You can see that the pilot vehicle is speed controlled and the implement is force controlled. That means when the speed is specified for the pilot vehicle, it is going to travel at a certain speed. You can imagine the scenario that if the implement's speed is different, then there are going to be a collision resulting in rise of very large forces at the point that joins the front vehicle to the back implement. But if you control this pilot vehicle as speed control device and the implement as force control device, then the implement controls these forces and adjusts its speed in such a manner that this force is maintained at acceptable level. That is why these two are differently controlled. And the implement has cost-effective sensors. It hasn't got any GPS or any complicated sensors. It is largely control systems only. The local sensing that is needed is there. However, the implement is very active, as you can see that its wheels are driven, and at the same time the wheels are steered. Now, in addition to this, there are other controls that we have in our system, which I will show you in a minute. However, they are driven and steered for the time being. And the coupling is high tolerance fit, so there is no play between the implement and the vehicle, but also it has sufficient compliance. You can imagine when there is no compliance between a coupling, what happens is the coupling forces suddenly rise and suddenly come down, and the controller that is trying to drive the implement is not able to cope with this sudden high frequency force changes. So therefore we need to have sufficient compliance in the coupling, right? So if we look at the machine, so I have it shown here. Let's see if I can move this. So there are some chats. Let me go and see what's in them. Okay, so they don't seem to be needed for us now. I'll minimize that. Okay, so this is the basic description of the instrument. So what you see here as a John Deere tractor, that is this part here, sorry. John Deere tractor that you see here is the pilot vehicle. And what you have at the back is the implement. So if you go from left to right, you can, first of all, you can see there is a steering sensor that senses the steering position of the tractor. And there is a steering actuator, which is just a little motor mounted here that turns the steering wheel. In normal modern situations, you can directly interface to CAN bus and send some signals, but generally it is very difficult to break into the protocols. And then there are two GPS systems that is going to tell us the position and orientation of the machine. There is a Wi-Fi antenna, which doesn't do much. Then we have these wheel encoders, purely for research purposes. There is an inertial measurement unit that is needed for the autonomous guidance of these machines. There's a box containing all the electronics. And then there is also this tiny antenna that is going to give us the GPS correction so that GPS readings are very accurate. So the implement has its own power unit, as I mentioned earlier, and then the hitch point has a force sensor. I will show you details of this in a minute. And the motors are driven using hydraulic motors. I'll show you details of them in a minute. And these wheels are steerable, and also the implement steering sensor is somewhere here, which we will also see in a few other pictures in a minute, right? So that's how this is largely instrumented. You can now see that the implement has controls. So I need to explain parts, so let me check pictures one by one and show you what they are. So first of all, let's take a look at the actual implement itself. So we know the tractor part is quite familiar to us, but this is the implement. So we have the wheels that are driven by these motors. I'll show you the motors in a minute. And there is hydraulic supply coming from the power unit. And these are all controlled by the central control computer for the entire system. So this wheel is driven together with that wheel. The way it is actually currently connected is that they both get the same driving torque, because we are force controlling this implement. By force control, what I mean is that the hitch point should maintain a certain constant force. So you can imagine if one of these plows dig into the ground, then it is difficult for the pilot vehicle to pull. As a result, the hitch point force will increase. However, we don't want that situation. We want the hitch point force to maintain constant, at a constant, regardless of what the implement is doing. So who is compensating for this additional load that just came on board because the plows went down into the ground? Then these wheels will take up that force and maintain the connection force, a force at the coupling, exactly as desired. So the pilot vehicle is not going to feel any of these things. All these disturbances will be managed by the implement itself, right? So the seating implements can be lifted up and down. That is one control. And I will explain you this control that we have here. There is another cylinder and a sensor that is up here. I'll explain you that in a minute. So this is the power unit that I talked about, and in this implement, which is a small prototype, we just have 2 wheels, but if it is pretty wide, you can have any number of wheels in the longitudinal direction, and you can have many plows in here. But the pilot vehicle is not going to feel that this is a huge implement, because implement is powered by itself, and all that power is used for implements all controls. So I will show you the steering system of this. I should be able to change photos here. So this is the steering system. You can see this is one of the steering axis of the wheels. The other one is over here. And there is a steering cylinder, actuating cylinder, and also a sensor. There's a huge tie rod here. So let's take a better picture of this. You can see how the steering actuator is. This is the Ackermann steering geometry here. And there's a big link here that is moving this tie rod left and right, thereby steering it. And we can close the position control of the steering using this sensor and that actuator. So that's how we steer it. There's more pictures of it, steering actuator and the steering sensor. And that's the steering part of it. So now we can go to the driving part of it. So this is the wheel. And there is a hydraulic motor here, and this hydraulic motor is controlling the speed. So this is the hydraulic motor, and the speed sensor. As a speed sensor, you can use the GPS, or you can use encoders. Now, encoders are not needed in a commercial product. You can use GPS to sense the speed. But the speed, as I mentioned, is automatically controlled by the force control of the drive forces. It is actually not controlling the speed. It's actually controlling the drive forces to control the coupling force at a constant. So this is how the coupling looks like. This is much more modern than this. I don't have photos that I took recently. So there is a little sensor here, a high precision sensor that is measuring the misalignment or the angle between the longitudinal axis of the tractor and the longitudinal axis of the implement. So that is measured by this sensor, and I will tell you why that is necessary. And this is the force sensor I was talking about, which is preloaded, so it can measure the force going up as well as force going down. That means the force that is occurring in this axis can be sensed by this force sensor. So you can imagine this force sensor as the sensor that develops the driving signals for the wheels of the implement. It does not do anything to the tractor. If the tractor pulls, the force goes up and the wheels begin to drive. As a result, this force comes down and maintains at whatever the desired value. So that's what the force sensor is. And there are 3 controls, as you can see here in this particular implement. One is to drive the wheels. The other one is to steer the wheels. And then there is also another controller at the back, because I was talking about that what we need is extremely high precision. And we want to get to a stage where broadacre farming is like a factory. Everything is precise. Machines travel very accurately. Everybody knows where the crop is. So you can reduce the sensing. Next time when you come, you don't have to sense. You just go the same way that you did plant them, and you will find the growing crop. So this third sensor is doing something special, and I mentioned that I will explain you about this cylinder and that actuator at the far end of the implement. And what it does is, if for some reason the implements, this trailer part shifted, let's say it shifted towards our left because the ground could not hold it, and then the misalignment sensor will sense that it shifted off the path. But that is okay. It can shift a little bit towards our left. However, we need to have these points, the implement's actual ground engagement points, very accurate. So this entire carriage can be shifted left and right by this actuator. So our software detects that the trailer or the implement went off the path by maybe 1 or 2 centimeters, and that angle will be sensed by the angle sensor, and control action will be taken by actuating this cylinder to adjust this implement so that the tools actually travel extremely precisely. So that's our requirement, that the tools really should travel really, really precisely. So that's the description of my, the hardware description, so I explain parts. And we can take a look at how this machine runs. So I'll play this video, I hope it will play. Volume off. So you can see that in order to demonstrate to you how accurately this machine runs, we have pulled a string. You will see this white wire, white string, 60 meters long, very taut, high tension, and we don't use it to control the tractor, but we use it to show you how accurately it runs. So if I play this video a little bit longer and stop maybe somewhere here, I will show, now you can see the string line. So this is the string line, purely used for demonstration of accuracy, not used for control. And we have a camera here. This camera is looking down towards the ground, and there is this aluminum angle in which we have placed a meter ruler. So the camera sees the meter ruler against this string line on the ground. And that way we can clearly show how accurately this machine runs when it runs. So let's watch this for a moment. This is a very long video, so I'm going to jump from time to time. You can see the force sense and all of that is here. So the wheels are being driven. You can see that it is very steady. It is not erratic, extremely accurate. And all of this is through the control systems that we developed. Most of these control systems are quite robust, because you can see that it is engaging the ground. Basically, there is no driver. Wheels are powered by the blue power unit of the implement. The pilot vehicle is only providing the guidance and all the control signals that are necessary for the implement. So you can, if you pay attention to the back wheels, you will see that back wheels actually steer at the far end. So when it goes to the far end, we will fast forward it. So it's traveled about 300 meters. And all the parts are planned. I will also show you how we plan parts for these machines. So our customers can actually generate those parts for their machines. So somewhere here, if you pay attention to the implement's wheels, obviously we know that the tractor's wheels are going to steer, but if you pay attention to the implement's wheels, you will see that implement's wheels also will steer. As a result of the turn that is coming in. So you can see that now they are steered towards the inside. So maybe in a minute they will steer more. Yes, now they have steered quite a bit in there. So it's lifted the plows, and whenever we lift the plows, we take force control off. Force control is quite unstable when there is a large angle between the two axes of the tractor and the implement. And as soon as it aligns again to the right field position, then you can put the plows down and continue this operation again. So let me see if I can move a little bit ahead and save some time. So this is, in a minute, it is going to show us the camera view that I described earlier, explaining the tractor's accuracy. So this is a tractor's, the rear axle of the tractor, how accurately it is following the path. You can see that, if I can stop this somewhere. So all of these darker marks that you see here, they are 1 inch apart. And all of these darker marks up at the top are 1 centimeter long. So this is the line that I described you, which is on the ground. Camera is looking past this meter ruler down to the ground. You can see that this doesn't deviate more than 1-2 centimeters at most. So most of the time it is within 1 centimeter as it travels. So this is traveling in rough ground, and it is engaging with the ground, pulling these plows, and you can see that most of the time it is staying okay. So I'm going to move this to further down to see how accurately the implement is going to travel. So this is the implement's accuracy, somewhere here, maybe earlier. So you can see that this is going to track by the seeding points of the seeder. So how accurately those points that are actually doing the work is going to work. So it is supposed to be at 300. So if I stop it here, if I can. So this is somewhere 300, this is 250, that is 350. So it's 50 millimeters here and there. It's supposed to stay on 300 mark, and most of the time, I'm sorry that it is not 100% clear, but it's 300 is here. You can see that the implement is traveling quite accurately using these control systems that we've developed. So that's basically, oops, somewhere here maybe, that's basically how the system works and keeps on shifting from pitch to pitch as it travels. So once it's plowed one set of lines, then it moves towards the right, and that way it keeps on looping and keep on going. So that's what that system is. So this is, as far as I can explain, how an active implement is operating out in the ground, out in the field. Okay, so let's move on. So we also have made other things. So these machines are not as complicated. We did this for one of our Chinese clients. These machines are not as complicated as you can see. It is not dragging anything. This is a 19-meter wide. So let me see if I can move this away from here. Yeah, I can take it away. So this is a 19-meter wide sprayer, boom sprayer. They are all folded now. But you can see this also, obviously, this is very smooth surface. However, you can still see that they are traveling very accurately. So what I want to do is that this kind of technology is not so this machine is very good. This time after the exact time around. So highly precise. So this is another machine that this is, as you can see, this is a tracked vehicle, a very small tracked vehicle, which is also for a Chinese client. These machines are really not conducive to be made to modern, state-of-the-art advanced machines. However, you can still develop very good control systems to deal with these machines. So unlike the other machines that I showed you a minute ago, this machine is taking square turns. So smaller tracked vehicles, obviously driverless again, they can take square turns. When they go to the far end, the other John Deere tractor took a circular turn, and these ones normally take square turns. And they are all programmed so that the system figures out when it goes to the right point, that it turns, lifts the plows up like the other one did, and takes a turn and aligns again itself and keeps going. So we just wait for this to take the turn and go around. So when you look at it, you will see that it is turning too much, but that is not what it is doing. It is actually turning 90 degrees to the path that it came. Obviously, the camera also moved. But when I show you the path generation software, I'll show you what it was doing. So now you will see that it turns almost 90 degrees so that it is parallel to the path that it came earlier. So, and then it speeds up. As soon as the turn is complete, it speeds up, puts the plows down, and keep going. So tracked vehicles as well as the wheeled vehicles, they both work equally well. So I'm going to skip this and keep going. So this is another, so a company that had an association with UNSW used our software earlier. You can see how fast these machines can work because they are so robust. As it comes to the turn, it slows down, takes a turn, and you can see the speed at which it is traveling. So this was filmed by chasing it after using a pickup truck. So it speeds up as soon as it hits the straight line. Obviously, it's a demonstration. The sprayer booms are folded at the moment. Okay. So as you can see that this is now becoming widespread, and it will be quite commonplace like the cars that we see out there. So one of the important aspects for all these people is the generation of parts for their fields. So normally they specify these coordinates. This is a simpler version of our path generation software. So what we do is whenever your client comes in, we give them this software. And this software they can use. Obviously, right now they are using a configuration file plus the coordinates. But in the future, they can enter all of these things in here. Then they, based on their machines and based on their turn types, then it will generate a path here. So let's see if we can run this path gen algorithms. So this is what you normally do when you start. There is no path, or system doesn't know where in the world this is. So when you say submit, what you basically do is you are sending these coordinates to a server that we provide to our customers, and then it will ask you to wait, and it will generate the path. So then you can get the path, and obviously you can save it somewhere. And so I'll overwrite that, and then it shows you where the path is. So to see some difference, maybe we can change one of these coordinates to some other number and submit. And also we provide them 3 different types of paths. So now it has, the server has generated the path and sent it back to us. We can get it. And so that's different because I changed the coordinate. And you can see that the turns are all circular turns because we were asking U-turns, but you can also ask for square turns. And if you submit, then it will give us a path that is generated for example, the tracked vehicle that we saw, it was taking 90-degree turns at the end of the path. And then we should see them all 90 degrees. Sorry. And so these are all 90 degrees. So this is why you saw that the tractor was turning more than necessary kind of things that we saw was one line was boundary, but they are not going to be. So normally we get another run that is along the boundary to cover the whole land. Okay, so that shows how the path generation software works. And it also tells you the network quality. Sometimes out in the field, some of the clients cannot use this. So then they have to, this will be read, and they have to go to their office and generate the path. And corner coordinates, if there is anything wrong with this corner coordinates, then it will also complain about the corner coordinates, and the path is ready. This will go green, then you can get the path. Okay, so that's the path generation software. And these are all available for customers to use, and they're very important. And also monitoring is very important. Well, we are not promoting monitoring that much, but once the machine gets going, so we've developed these situations where the clients can log in to their machines by logging into our server, and their machines are sending the data to the server, and they can watch the behavior of the machine by logging into our server. And here it says what is this current speed of the machine, how much fuel is there, how much water is there, how much chemicals are there. This will show how many satellites are actively connected and so forth. So this is for them to monitor what's happening with the machine. We also did some research on bulldozers. Bulldozers are very robust machines, much easier to control than tractors because their ground holding is really, really good. Precision is still important in bulldozers. So in mining, for instance, you have these lines of bulldozers, and why they have these gaps between them is because they are not precise, driven by drivers, and they can collide, leaving all these windrows. However, if you can actually run them very precisely next to each other, and then you can actually avoid having to do this job over and over again because of the windrows. So these kind of vehicles are also used in agriculture, which is one of the very popular agricultural tractor that is used by large farms, which is a challenger of the Caterpillar company. And you connect all these implements to this. These large vehicles don't take square turns, they take circular turns. However, they are very good machines. So we can discuss a bit of why we do all these things. Now, if you look at the automated machinery and autonomous machinery, the automated machinery, they are able to react to sensing, but the unexpected circumstances are very well known. There is no surprises in them. And all decisions are built in, largely coded, without having to go through any intelligent software. Whereas autonomous machines are slightly different. There is a wider variety of sensing is needed because the unexpected circumstances are not entirely known. So adequate software technologies must be there for decision making. Now, why autonomous? One of the reasons is to replace human. Everyone thinks that we can get rid of human, and that is the main aim, and that is where the money is, which is quite incorrect. It obviously reduces the labor costs, but in a country where labor costs are very low, then someone is going to ask you, why get rid of the labor? Because it doesn't cost us anything. So that is not a driving factor. And elimination of human error, because if humans cause elimination of human error from the safety point of view, you cause collisions and you run the engines in an inappropriate way, therefore their durability comes down, and all these things. Yes, there are some useful points, but the real points are the exceeding reasons that go beyond human capability. For instance, the precision unachievable by human operators, the precision that I showed you against the taut string as the machine traveled along. Who can drive like that? No one can drive like that for 10 kilometers. It has to be autonomous. Endurance. Who can sit in this machine day in, day out, traveling 10 kilometers that way, 10 kilometers this way, 10 kilometers that way, 10 kilometers this way, continuously is very tiring. And what you need to do is to save the operator, you have to stop the machine, and that machine is capital. So you are tying down the capital to care for the human operator, which is a very good thing to do. But if you can get the maximum benefit out of the machine by running it around the clock, you should be able to do that, and a human cannot do that. Repeatability. How can a human sense it and repeat exactly the same thing? It can't do that. And the situational awareness, there is only a limited amount of knowledge or data that our heads can handle, our brains can deal with, whereas these computers can deal with large amounts of data, and they can do incredible things that we don't do just because we are unable to do, or we didn't think about that we could do these things. So there's a lot of data as well. So I'm just checking time, okay. So 10 more minutes about. So precision in autonomous agriculture machines. Why precision is needed, especially in agriculture? So crop can be planted according to specified layout. Knowing crop location drastically reduces sensing. So if you have to go into an agricultural field, from the get-go, you have to start sensing to find out where this crop is, and that is very expensive. Sensing is actually one of the most expensive things that we do. Knowing crop locations drastically reduce wastage in substance application. That means if you're applying fertilizer, if you don't know where the crop is, you have to fertilize the entire field. Whereas if you know exactly where the crop is, then you can direct your fertilizer to the crop. As a result, the fertilizer usage can be cut down by about 2/3, nearly 2/3. And someone who's spending $1 million on chemicals or fertilizer, if it is cut down by 2/3, you're already saving $660,000 in one season. And that is about, with that money in one season, you can cover the cost of this machinery. Maintaining structure further facilitates automation. That means if you plant these things very, very accurately, then you already eliminated sensing. Next time you follow exactly the same path, applying fertilizer to exactly where the crop is. So if something is very structured, then automation is easier. If you use automation, it becomes structured. Structure helps automation, and so forth. It becomes almost like factory-like after some time. And also the crop damage can be avoided during subsequent operations because you exactly know where you planted the crop. It's always planted according to pattern, and you can now blindly drive without worrying about where the crop is because you planted it very accurately to start off, right? So precision autonomous agricultural machines, why is it so hard for us to do this? What makes a machine precise? That is being able to do the same thing over and over again. So we had to obviously use high accuracy, low noise sensors, data fusion, and localization, and all of those things we know, but we can't position this machine on the path all the time. Why? So here is an example. You take the train on the tracks, there will always be more than enough lateral forces because the train wheels are guided by the tracks. So always, the train is never going to slip sideways. Why? Because the tracks are providing sufficient forces. The train does not steer itself. Agricultural vehicles steer them, but train does not steer itself. It goes through a curve quite nicely. Exactly, precisely, because the tracks steer the train. And these lateral forces, the exact dosage of lateral forces required to steer the train is delivered by the tracks. So train always go exactly on the same path. And if you're trying to get the tractor to do this, it is not going to work like that. Why? There will often be not enough lateral forces to hold the tractor on the path as it traverses. Soft soil gives way and tractor shifts sideways. Tractors steer themselves, demanding the ground to provide the lateral forces, and the ground fails to deliver sufficient lateral forces, not like the rail tracks. So the mismatch between the lateral forces provided by the ground and the required by the steering causes the vehicles to deviate off course. So therefore, we go and design control systems or find other solutions, and all these machines, in comparison to the wheeled vehicles, these machines have very long contact patches and their ground holding is really rock solid and they don't get shifted that well. Same with these delta tracks, this kind of tracks, these are steerable and you can use those tracks and you can also drive them. So it is not only that you can bring it back through not slipping, but also the drive forces can be vectored back to the track. And these are very good methods to avoid sideways shift that destroys the crop layout in soft soil. And these four-wheel steer, four-wheel drive systems are also very good, that you can have modular steering. So this module is completely independent of this module and so forth, is also a very good solution to keep the machines on track. So we have a machine like this in our lab, which is going to be entirely force control. You can see 4 force sensors, one there, one here, one there, and one there. So at any time, we don't have to estimate anything, predict anything. We know the real forces that this machine is undergoing. And if you know the forces, you know how to control it on the track, along the path. And you can adjust these forces through control systems. So we have done these nonlinear robust control methodologies, the sliding mode controllers with force observers and slip observers, as well as model predictive controllers and various other methods that we have used. So we have published them in this book. This is my PhD student, Javad Tagia, who finished his PhD about 3 years ago. So this has applied guidance methodologies for off-road vehicles, which are the algorithms that we developed over many years. So we published this about a year or maybe 2 ago. Right, so as far as safety is concerned, consider what we provide as autonomous vehicle designers. We provide steering, propulsion, and implement control. But what really causes injury or damage is propulsion, how you drive this. So you need to make all these safety provisions. And there are 2 levels of execution. These are the SAE 6 levels. And they are divided into 2. You have these 2 levels of execution, that is steering and propulsion. It is driven by a human and steered by a human, or driven by a system, which means a computer steered by a system. And 2 levels of monitoring. Who is looking after the machine? Is it a human or is it the system itself? And 2 levels of fallback. When the automatic system breaks down, is it a human who is going to take control, or is it the system who is going to take control? So level 6 will be system is doing the execution, steering, and propulsion. System is doing the monitoring, and the system is taking it over. It is very difficult to do this in an urban setup, but in the field scenarios, this can largely, this realization is quite close. We can actually achieve this. Because all these dangers due to motion is quite subdued and reduced. Therefore, we can actually do that. There are no urban canyons, good GPS reception is there, mostly flat land, there are no humans, a widely open field, and all of these things added together gives us very close to level 4, 5, 6. Well, we're not there yet, but at least level 4, level 5 is quite easy. So finally, to finish, so we have another 5 minutes or so to go. So of all people who try to use autonomous vehicles, we are better because, especially those who develop autonomous agricultural machines, We mostly operate in private land, so we are largely immune to litigation, various legal action, protests by people, and so forth. Is largely not against us yet, or may not be ever in the future. The land is mostly sparse. You don't have to consider collision avoidance constantly, but you must have collision avoidance systems put in place in these machines, but they play a minor role. The agricultural terrain does not allow hazardous driving, such as in mining. In mining, it is very dangerous. So you need to have very well controlled exhaust control, sparks and things like that are very dangerous. So mining is much harder operation than agriculture. And we do not have to confront hostile unknown scenarios. We are not fighting wars. This is very peaceful scenarios. That's another positive. So our operations will always be to make people live. So it is quite rewarding than to kill. So therefore, agricultural automation has a very good future. It's quite possible to achieve. And I'm pretty sure that very soon, there are already agricultural machines slowly operating in the fields. This will be quite widespread as time goes on. So that's the end of my presentation. If you give me 1 minute to look at the messages to see if there is anything that I need to answer. Okay, there are no questions here. I don't think, okay. So there's one, let me see if there are how many questions. That's not. Okay, I got one question. As the implement is attached to the main vehicle, how do you control the path of this implement to accurately follow the path of the main vehicle, especially when it is maneuvering? It is very important. Yes, it is very important. We are now currently working on similar case. That is Tugger train system, which is quite similar to your system. Thank you very much. Okay, I will see if there are similar questions. That's no question, not for me. Okay. Yes, this is quite important. So what we actually do in our system is that we have two controllers because we have more degrees of freedom that we can control. Like we can steer and reposition the back vehicle as well as the front vehicle. So they're both steerable. And we implement almost the same controller for the tractor's important point that is following the path, as well as this implement's important point that is following the path. So of course there is a constraint at the hitch point. However, largely because we can steer the implement, we can maintain the implement's point of interest on the path. Provided that we don't have extremely sharp acute corners and so forth. So we actually implement two identical controllers. The details of this you can see in the book if you look at how that is done.
Thank you, Professor. Thank you very much.
Please go ahead.
Thank you for thank you very much, Professor J. Katupitia, for addressing this interesting topic on, we could say, high precision farming. I hope everyone here gets every detail from the presentation. I may have some questions. In the presentation, you state that the commercial usage of the vehicle doesn't need any encoders for the positioning. Is it true?
Encoders are actually not used in the commercial products. We did not use encoders, but I mentioned you about slip observability in some of our control systems. So at that time, we wanted to see how much slip is taking place. For that kind of measurements, we use the encoders for both. So you can actually take the GPS generated path and the encoder generated path, and the differences between these two tells us how much slip is going to be there. You can actually estimate the lateral slip by measuring the encoders, because you can plot the encoder generated path and the GPS generated path, and the lateral shift is going to give us the actual slip. You can do that in real time.
see. Thank you for the answer. And one more question. There's a question from Unpar, maybe here. Wait a minute. What is the maximum range of the autonomous pilot tractor?
Maximum range?
Yeah, maximum range.
The distance that it can travel?
Yeah.
It's as long as there is diesel, it will travel. So not this small green tractor, but the orange tractor that I showed you, we ran it for 8 hours non-stop.
Oh, that's long enough.
Yeah.
Okay, is there any question from the participants? Okay, we have a hand raised from Muhammad Abu Malik.
Thank you, Professor Jay. Just have a quick question. Like, I understand you use the GPS for locating the vehicle. So if my application is in narrow space, you know, GPS error sometimes can be around meters. So can you please elaborate if I decide to go with sensors or like IMU in terms of, getting position, maybe velocity. Just if you can elaborate on using IMU instead of GPS based on your experience.
So the problem with the IMUs is that the quantities that the IMU is sensing is acceleration and gyro rates. So gyro rates are very useful if we are on a drone or something like that, but on a ground vehicle, gyro rates are not that useful. So it is the accelerations that we measure. And if we need to eventually localize it, we need to know the XY coordinates of this thing. However, most of the accelerometers have these biases. And if you have a bias in the sensed quantity, acceleration has a bias. So when you integrate this to get the velocity, the bias gets integrated and the velocity gets shifted. And then when you integrate it once more, then you get the position. Bias is twice integrated and your position reading is quite wrong. So only thing we can do is if every now and then we can hook on to a landmark that we know of or we have seen before, then using the landmark details as the position fix, when the landmark is gone past for about 7 seconds, we can keep going with the IMU. But after some time, IMU reading has deteriorated again. And so one of the best things that we can do it's like in a wide open space, this is certainly not a problem because there is good GPS. And on the other hand, there's nothing to sense because you will not see anything. But in the situation that you are describing, then there are a lot of things around you, but GPS is not one of them because GPS is partially covered and it's not giving you very good readings and so forth. So scan matching is one of the very good methods that you can use. That means you take a scan of what you see and move a little bit because you are constantly taking these scans at a very high frequency. Then you get a new scan and then you can match what was the old scan. You will only see part of the old scan in the new scan, but you need to identify that part that you saw in the last time instant and that you saw now. And then you can shift and match these two parts that are common, and that shift generally, the rotation and translation that you need to do to get the old scan to match the new scan or the new scan to match the old scan is generally a very good indication of how you moved. So scan matching is one good way of doing it, or you must have landmarks. Landmarks also can be illuminated strips, for instance, that you saw last time and you're seeing again in this one. So how positioned it is in your scan, and that way you know by how much you turned and by how much you moved. So that is the only the fusion of GPS and IMU is only useful when GPS for short periods of time when GPS disappears. IMU GPS fusion will be good enough for you to survive until GPS comes back again. The data fusion with GPS and IMU is really not a good solution when you don't have very good GPS.
Okay, thank you for the answer, Professor Jay. Is there any more questions? from the participants? We do still have 10 more minutes. Okay, I think this will be the end of it. Okay, once again, thank you, Professor J. Katupitia, for sharing the information. We'll be going to the next, the secondary session.
Okay, thank you so much for inviting
Thank
me.
you, Professor J.
Thank you.
And
Take
my
care.
Rika from Bandung.
Okay, thank you very much. Bye for now.
Indonesia traditional culture is very rich. We have so many cultural performances. As Bandung resides in the land of Sunda, we would like you to enjoy one of our traditional dance performance. It is Jaipongan dance, which exhibit enchanting movement of the dancer. The next Jaipongan dance performance is named Bentang Bandung, which show the beauty of Sundanese women. Ladies and gentlemen, please enjoy Bentang Bandung.
Bintang Bandung, bintang Bandung, bintang Minang tinggal di langit Bandung, bintang Bandung, bintang Bandung, matak nari ambil bintang Bandung. Mojang ngejang pilih
Welcome to Parahyangan Catholic University, where knowledge and experience are sought and great ideas are highly valued. This is the place where traditions are nurtured and history is made. Located in the mountains of North Bandung, UNPAR strives for advancement and innovation in 16 fields of study, namely economics, management, accounting, law, public administration, business administration, international relations, civil engineering, architecture, philosophy, industrial engineering, chemical engineering, electrical engineering in mechatronics, mathematics, physics, informatics. UNPAR provides an accommodative learning environment that creates outstanding graduates who are responsive to current opportunities and challenges. This is the campus where all dreams are inspired and passions are pursued. Through a continuous desire for excellence, achievements after achievements are made possible. UNPAR is a place where diversity is respected and community is built. Divinity, truth, and integrity have become the foundations of our academic culture. With various extracurricular and campus activities, UNPAR has been able to provide a comprehensive education while building the essential virtues of thriving in the present and preparing for the future. With decades of experience and solid foundations, from generation to generation, UNPAR has been recognized at national, regional, and international levels. We proudly acknowledge our professors for their expertise and our staff for their dedication to service. We heartily embrace the trends in digital transformations by adapting to current and future needs and challenges in the context of education. UNPAR believes in developing local potential on the international level. Thus, internationalization is an essential part of our commitment to provide our students and staffs with the needed exposure. This commitment is supported by high-quality facilities and infrastructure throughout the campus. Our efforts towards the future are guided by the spirit of Bakuni Yangri Guna Sunchaya Bhakti, understood as based on the belief in God, the advancement of knowledge and devotion to the community. Compassion and humanity have become the center of our academic endeavors, which are ultimately dedicated to society. Welcome to Parahyangan Catholic University, the answer to the future. We begin here and now.
Dear all conference participants, our second keynote will be delivered by Professor Maki Habib from American University in Cairo. The topic is Bioinspiration, Intelligence, and Autonomy. Dr. Bagus Artayo will be the moderator of the talk. Without further ado, Dr. Artayo, please guide us for the second keynote.
Good afternoon, ladies and gentlemen. Distinguished guests, Professor Maki Habib, welcome to virtual Bandung, I would say. And all participants, I would like to give you warm regard from Bandung. Right now, we will follow the second speech from Professor Habib. Firstly, I would like to read the biography of Professor Habib. So Professor Habib obtained his Doctor of Engineering Science in Intelligent and Autonomous Robotics from University of Tsukuba in 1990 in Japan. He was selected research scientist at Riken, Japan, and senior researchers at Reiso Laboratories, Japan, and also visiting research at EPFL, Switzerland. He was a visiting professor at the Asian Development Bank, associate professor at UTM Malaysia, and a senior manager of MCRIA for engineering, project, and industrial consultation Malaysia. He was a leading senior research scientist with GMD Japan leading telecommunication research group. Associate professor with Monash University, Australia and Malaysia. He developed and led the mechatronics engineering program. He was appointed as a full professor of robotics and mechatronics at Swinburne University, Australia, Malaysia. And he was an invited professor at KAIST, South Korea, residing professor at Saga University, Japan, and since September 2007, he is a full professor of robotics and mechatronics at AUC, American University in Cairo. And Professor Habib was also a visiting professor at many universities around the world, such as Nagasaki University, Japan, Hokkaido University, Örebro in Sweden, Norwegian University, and other university related to Toyota and ABB. Professor Habib also served as editor-in-chief of the International Journal of Artificial Intelligence and Machine Learning Regional Editor, and associate editor of 10 international journals, an editor board member of another 10 international journals, besides his leadership as a member of international organizing a program committee of more than 20 international conferences every year. Professor Habib edited more than 14 books, published more than 26 chapters, and also more than 275 papers at international journals and international conferences. I think now we are all curiously to hear the speech of Professor Maki Habib. Please, Professor, the stage is yours.
Thank you very much for the introduction. It's my pleasure actually to be here and joining the conference, the MOSI conference. And good afternoon to all of the audience. And I hope that through my presentation you will enjoy it and having some of the information that will help to guide your research. So I will try to share my presentation. So the title of my presentation is Bioinspiration, Intelligence, and Autonomy. And here we are reflecting all of the three keywords for the bioinspiration, intelligence, and autonomy in association with the field of robotics. So you know that the evolution of robots or the field of robotics in the recent modern era started in by the end of 50s and early of the 60s, and the main development was focusing on industrial robots, and then the dimension of the research in the field of robotics start to expand to cover ground mobile robots in all aspects of it, sea mobile robots in all aspects of it, aerial robots, drone in different types of structure, from micro to larger scale military one, humanoid robots, biomedical robots. We have a service robot, and normally service robot is growing to go to the different dimensions actually, that you have a robot that can replace a human being, you have robots that can work on human being, and you have robots that can work together with a human being. This is actually evolving toward the development of a personal robot, especially in the developed countries where the aging population is growing, and they need to have support and help. But the lack of people actually to give such as services is not actually facilitating such help. This actually opened the way to develop robots that can, with the shape of robot, with affections, that can work together with human being at home. Also, the development expanding to the space and expanding also to the here is the first key word that in my talk I will talk about the bioinspiration, because there is a limit of the conventional way in the design, and the bioinspiration will open a new actually spectrum to look to the nature as a model and develop new design and structures supporting by eco technology actually that will work in harmony with the environment while supporting humanity. So these are quick examples actually about the industry. You have industrial robot for welding. Mainly actually you have industrial robot widely used in the automotive industry. Heavy number as you see it in the production lines. You may see it in the painting very widely. If you see now the large companies in automotive may produce more than 12 million cars per year for a single company, and that's by having human alone would be very difficult to reach such a number, but by automating that process, using a robot will be essential in terms of quality and in terms of speed and in terms of cost. These are examples of painting, different types from external and internal painting. This is cooperating. You have two robots that can, or multiple robots that can work together to cooperate doing a joint task. Here is the sophistication will come when you are developing fingers with a force sensor that can interact and detect the object and take care of a soft object while interacting with it. Also, there are some breakthroughs actually started by 90s, end of 90s, and now up to now actually is continuing, is to develop a mechanism, especially starting with Honda when they developed the humanoid robot, to have a humanoid robot that can freely move without having it being chained to a structure and being afraid from falling down. So Boston Dynamic later on is making a big breakthrough actually in terms of design structure and mechanisms. This is one of the example actually is a bio-inspired by animal of 4 legs. Having this is the base of the robot, and you can integrate to the robot different things. You can integrate a robotic arm, you can integrate for surveillance, a camera and sensor. You can have a gun for security if you are conducting a surveillance in a high value zone. So this actually it's and the key issue actually of these in the design is the recovery. Recovery mean when it is falling down, it will not harm itself while it's going to recover and stand again and conduct the task properly. This is the already evolved design of the first Honda robot, but this is the latest one. It is telling us it's not just moving freely, but also it can interact with a human being through natural language. Can through a camera here, stereo camera at the face, can recognize faces and associate or talk to them or cooperate with them for a specific task. These are the robots of Boston Dynamics, in which actually the humanoid actually can work on 4 legs and can work on 2 legs. It's easy to recover. Jumping and running for a humanoid robot is quite a critical issue. And Boston Dynamics, this is actually a main breakthrough in the development of a humanoid robot, where the robot can run and cross obstacles without actually being slowing down. And also, if it's failing, it will has the ability actually to recover. Sure, when you say have the ability to recover, I mean there is something inside the robot can recognize this situation and recover from it. So it means there is sensing capabilities, information, perception, cognition, and reasoning about the situation. And this should be done in a very fast time. That's where the computational issue and the evolution in the computation is critical actually to deal with such a big amount of information in order to reach a decision with a very, very small amount of time that will enable a robot actually to conduct its job while avoiding obstacle and harms. Also, in the future, or not very far future, you may have a humanoid robot working either alone in certain factories, especially for the factories that are critical in terms of safety for a human being, or it can work together with a human being within the same shared space. You may also see, not far from now, I mean within the 10 years, possibly, or a bit more, robots within small shops along the road to deliver services like a beverage or food or sandwich or etc. Also, there is a you know in the after the 2000, all of the evolution and the development in the robotics area started from science fiction, and then from the science fiction, researchers start to, while the technology is evolving, try to develop and try to adapt the science fiction idea and put it in reality. So this is a movie actually called Surrogate, where being introduced as a robot representing human being with all capability of sensing, but all of this information will be sent back to a station, and the actual person is interacting with this person, and which I mean, this is the robot side, and authorize the robot to act on his behalf or her behalf according to the need. And the robot, once it's done the work, will return back to a station to charge itself. This is how the movie actually show the situation. And after the movie, normally people start to have it as a humanoid moving outside, and there's information coming, collected to the station, and the person actually is interacting. Sure, at the beginning will be limited capabilities and limited functions, but gradually, as in any research, you are building the platforms, establishing the essential functionality, and then, as in all research actually, it's like accumulated the process that you are building up gradually to reach better and better according to the level of development. Here, they started also during the last 10 years or a bit more, is to develop, which is mimicking the surrogate actually, to develop robots mimicking human being, and especially when we are talking about personal robot, a robot that's going to work with a human being at home, or interacting through human aspects of affection. So they develop, especially if you see in Japan, this was in Japan, developed a robotic character mimicking human being. And that is a base for future to have a personal robot living with a human being at home. If you are thinking about the developed countries, the rate of people living alone is increasing in a rapid way. And there is a need, because now helpers, young helpers actually, are refusing to extend or participate or be employed in a job for supporting a service for elderly people. And that's a critical need actually, to have people or robots actually to do the job. Since the people are not available, then the other alternative is to develop robotics for this purpose. And the space actually, instead of having a human flying in the space, so you have a robot actually mimicking human that can fly and move around to conduct a certain maintenance or monitoring or specific required action within a specific mission. And this is the well-known guy who started this area of developing a robot that's mimicking human being. And this is the robot side, and this is the actual person. He's a professor at Osaka University in Japan. Also in Stanford, they developed a humanoid robot, the submarine type, that can communicate and interact and act under the sea. There are different types of submarine actually with different capabilities. A submarine that can be being integrated with human being and go, or submarine that can have no human being but with limited capability in decision making that's still required to have a human to be in the loop. And you may have a submarine that's completely autonomous, integrated with different types of sensors that can go for a specific mission within the sea environment. Also, the development being extended beyond the submarine and the ground to the flying robot. And the flying robot, Festo actually developed a bird with the flapping wings. And also you have a micro level of flying robot being developed. And actually, I am personally engaged. I have a master's student is developing a flapping drone that can normally the size of can be different from a very micro level to a large scale flapping. And Festo demonstrated this one in a very successful way. If anyone can check the YouTube and can see the demonstration of this bird perfectly. Also, the development of quadcopters as drone now is increasing from micro level to a large military level, and in between you may have a lot of different capabilities. And not just using a single drone or single quadcopter, but also the integration between different quadcopters. In my lab, actually, we are developing different structure from micro level to a large level quadcopters for different possible mission. Mainly now we are focusing on the control and the navigation to generate the required trajectory and cooperating between multiple drones. Also in the military, it has the big actually consideration of adopting robots within the military, from the fighters, planes as aircrafts, to the ground tanks, missile launchers, and also to adopting actually a humanoid soldier. So you have it actually, and all being coordinated, because the capability of communication and integration to cover a large area is essential, and they are developing a lot of things in this domain. Robots can cooperate among themselves and can cooperate with a human being for different purpose. So this robot has a dual arms. It can do the cooperation between the arms to conduct the job, while here you have a multiple robots can work together to coordinate the job and complete it successfully. Also, robots, as I mentioned earlier, for the personal robot, it's coming in different shape, in the recognition through the camera, in the natural language interaction, in the supporting for elderly people at home, and the entertainment, etc. this is another example for a medical type support, which is exoskeleton. Now it is widely used in many hospitals around the world to support people that have problem with their motion capability. And here is the delivering of food for different purposes, whether inside a hotel or at the hospitals, etc. And you may see in the future a doctor robot that can go and diagnose and collect information. Here is a surgery. This is very widely used nowadays, actually, and it's been proved successful in terms of accuracy and time recovery for after the surgery, because they are limiting the details of the surgery on the body of human being. And that's why the recovery time would be fast. This is the nanorobots. Actually, I have a PhD student working in developing the structure and that's going to control a nanorobot, and he is almost at the end of concluding the three-dimensional control of a nanorobot to move the intention, but not because we are mimicking the operation to move in the vessels, mimicking human blood vessels and the operation. In the future, that's already started in the movies. You may see a lot of movies actually where the robot or being integrated with the robot human organs. And one of the key organs actually that's been integrated with the robot is the human brain. That's appearing where in the science fiction movies. So in the future, actually, there's a possibility, while the technology is evolving, there is a possibility to realize these things. And beside that, also, since the robot is very accurate and repeatable, then it is compared to human being, because human being, normally the accuracy of a hand cannot be sustained, and it is associated always with error. So having a robot to go to a specific place within the brain and inject a medicine is not easy to be done by a human being, but by a robot, because at least you have now robots accuracy reaching to 1 nano or 1 micron and below the 1 micron actually, then the damage caused to the brain will be very minimal compared to human beings actually. So as this general introduction about how the robotics field is evolving, and it's open actually, it's open ending. No one will actually can exactly know where we are heading exactly in the future. And because everything from my point of view, except the soul of human beings, anything beyond the God capability is possible to be done by human. Because God is facilitating these things for human to learn and develop things and understand the surroundings. And facilitate, not just understand, facilitate what is available in the nature to support his or her life as a human being. So when we talk about bioinspiration and creative design, in the 21st century, the difficulties, actually the challenges is associated with the complex environment. Complex environment, especially when you're talking unstructured. You're talking to open space, not through the road. The roads still are, car roads are still manageable. But when you are going off roads in open area with rocks, sands, mud, so these are very complex operational environment that need to have a creative design and development to enable the robot to work freely and effectively within such environment. Also, the 21st century, the challenges within the 21st century is telling us or indicating there are a lot of problems or pressures facing human beings at the social life, as I said, for the elderly people and how to serve them economically and environmentally also. So there is a pressure actually caused by all of these things because we are developing a technology that's affecting possibly negatively on the environment. So it's how to develop eco-friendly technology, whether it's for robots or for other mission-related tasks, to support such aim is to have a little impact on the environment, to have them sustainable. So the design should be sustainable and eco-friendly in general. So these need to be dealt with, and to deal with these things, it is required people to, which is when you say people, I mean mainly people working in the field, to be creative, to think out of the box, not to limit ourselves with the conventional aspects of design, to be native for new ideas, to be adaptable for any possible new information, knowledge, to adjust the design process, and to have the motivation and confidence in having effective thinking capabilities. And I'm always linking these things that saying conventional way cannot do that, cannot do the job. So who is going to do the job is that when you think about modifying or reusing already tested design, which is the conventional one, we cannot meet the requirement. And that's why we need to face new challenges. What is the new challenges aiming for is to design and solve new engineering and science problem that demand effective and agile solutions. Who is going to contribute to that? Conventional way, it will reach to a situation. So there should be another way of thinking, another way of creative approach to have to deal with this situation. I believe always, as a person working in mechatronics for the last 32 years, that mechatronics is introducing the solution, because mechatronics represent a philosophy more than a technique. Is a way of how to deal with the thinking aspects and with the development aspects, and how to integrate all of that together to develop new, to stimulate thinking and develop new ideas. So that's why, as a definition of the mechatronics, I'm just putting it in between, is regarded as a philosophy that is still stimulated synergy. Because always, I believe, when you are defining mechatronics, I'm not calling it integration of different disciplines. No, I'm calling a synergy of knowledge from different disciplines, and that will support the design development. And such approach is featured by what? Interaction of open-ended interdisciplinary knowledge. There's no limit in mechatronics to stop at the knowledge, because it's open for all aspects of knowledge, as long as it is required to consider such a knowledge in biology, in chemistry, in electronics, in computer, in mechanical, in construction, whatever knowledge that is benefiting your thinking, to develop new ideas, you can adapt it actually as interactive knowledge requirement to reflect the interdisciplinary aspects of it. Building up a thinking skill through learning. And this is very important skill actually, because thinking is a skill that can be developed in a human being. And the mechatronics way of learning can establish such aspects of a skill. And we can have a skill in terms of creative thinking, and we can have a skill in terms of critical thinking. And both of these actually can be established and built up in our programs and have it actually developed in our student ability. Stimulate creativity and innovation, achieving best functional synergy. And this is a key point for mechatronics, because it has a concurrent design, then essentially the synergy in the design will not come individually at each section of the design, rather than it will start from the beginning of from the conceptual aspects of the design process and work together until reaching the target. So apply concurrent design methodologies, develop dynamic way of work supported by practical and communication skills. So mechatronics creative design use nature for the supporting the bioinspiration as a model of inspiration that will help to have a conscious abstraction of new principles from the nature, idea, methods, tools, inspiring creative design. And for what? To understand the condition and allow such approach to produce innovative bioinspired design that help to transfer idea from nature to engineering. So the key principle for that, or the design principle in this case, help improving design process and find best possible solution for each design scenario. Now, when you come to there's two aspects, in the literature, you may see people calling the bioinspiration as a biomimetics because they started with this word. Personally, I prefer to use the bioinspiration because biomimetics is to coin, to duplicate things. Bioinspiration, it may include the duplication, but it may include only to abstract idea and knowledge from the nature, not necessarily to duplicate it, rather than abstract different algorithms, different material, structures, etc. So, and accordingly, we can define the biomimetics as an interdisciplinary scientific research field characterized by technology outcome, which is normally related to hardware development and software development, not limited to hardware. So it is reflected in all different fields, as I mentioned: biology, physics, chemistry, information data analysis, data science, and nowadays we are having the big aspects actually of a data science, where a big data now is coming in and need to be processed carefully and effectively, supported by different learning algorithms or techniques. So bioinspired design reflects interdisciplinary synergy. And the aim here, when you are talking about nature as a model and thinking about the bioinspired design, we are actually considering the aim of that to achieve sustainability. And sustainability in terms of environment and resources. And this actually, the aim of to achieve sustainability will lead us to the development of sustainable design principles. So that's why bioinspiration is the solution actually for a lot of problems in the coming future, especially when you are dealing with environment and resource. And actually, I'm working with the two colleagues from Austria and the UK in having a joint book about eco-mechatronics. Is how to consider actually environment, resources, in developing new technology that is not going to harm the environment. So the point here is not only developing a technology, it's to develop a technology that is sustainable without adding harms or more harms to the environment. So nature as a model is guiding to source knowledge and inspiration and help addressing sustainability and applying it in the development and practice of sustainable design. And this need to establish actually at the educational level, at the researcher level, a sustainable design thinking. Biomimetics, a concept, I will just go through it quickly. Help conscious abstraction of a new principle, foster innovative design, find out new techniques and functionality, seek new paradigms, develop a new material, actuators, sensors, design a new stream of intelligent machines. So we have different level of the bio-inspiration. You may abstract aspects from nature. You may develop new appearance, shapes, structure, and this happened for the sea submarines, cars, airplanes. So all of these actually been abstracted from the nature, from different animals, different structures, etc. Mobility at different beings living in our nature. Intelligent operation, thinking, decision-making, sensing capability, control, brain and decision-making, reasoning, formation, when you are dealing with a not a single entity, but multiple entity working together to achieve the target, and speech and understand, which is this is actually coming as a very hot topic nowadays. When speech and there's a natural language interaction, which is related to the human-machine interaction, and that is essential. Will actually bring us outside from programming a robot to do a task, rather than you can interact with the robot through the natural language, and the robot will understand what you want and learn, and then can do the work accordingly. So all of the mentioned technology that contributes to the progress of biomimetics are highly interrelated and heavily synergized. And these are examples actually of, at the structure level, the shapes, the material, at the mechanism level, behavior level, sensors and communication, and generational biomimicry. So you have a different example here showing that how up to now actually people consider the nature as a model to develop varieties of things. This is an example that's very attractive, because if you see in the nature, there is no motor rotating. All of the actuators are not rotating in the nature, but artificially we are developing an actuator that is rotating. So the alternative, all the animals, and they have muscles. And people start to think about developing artificial muscles, mimicking human muscles, at least at the beginning. And the performance of the natural muscles for human is stated in line 1, where here the strain, actuation, pressure, density, efficiency, etc. And there are different techniques being used to develop things. Electromagnetic, you have some deficiencies in covering it, but the best development here, according to Stable, is the dielectric elastomers. That is almost mimicking human muscle. But does that mean that it will be the best to replace every application? The answer, no, because some of the application you need to have a very high torque, and you may use some of the currently available actuators for this purpose. But if you want to have a more flexible, effective way to conduct, then our human being is very, when you're moving our body, moving our arms through the muscles, very smooth and accurate. This is actually how using different types of muscle, and you can move this diaphragm in the way that you, and this is the electroactive polymer type of actuators. Now, coming to the second point quickly, seems the time is running. So robot intelligence, the need for intelligence, what? To enable a robot to interact and cope with the operational and task environment, to support reliable and effective execution of an assigned task, assess successfully conclude the final result and assure safety, exhibit emergence property. And this normally because through the intelligence, a robot can learn and add a new knowledge, a new experience, and not limiting itself to the previous functionality. It will add at the top of that with emergence capability that is coming through the experience and the interaction and conducting any given task. So why the robot needs sensors? These are a key element actually of intelligence. Without sensors, neither human being, neither any species actually can have an intelligent action. So through the sensor, whether it's a sensor as proximity or sensor with diversity, all of them are essential to have it, to build up the experience, to enhance reasoning through the data that's being collected, and to have a proper decision making, and achieving not just the decision making, also to follow up the action being taken, assure the accuracy, the efficiency, and the safety of these actions. So that's why the robot needs sensing for the purpose of task itself, to execute it, and it needs sensors to cover the need when the robot moving in the task environment, and it needs to have sensor to sense the robot internal structure as a configuration and its relation to the surrounding when there is interaction with the surrounding. The question may be raised actually, what kind of information the robot can collect and how to deal with these information, the meaning that how to abstract information from it to represent it, and this can be used in reasoning and decision making. So collect information, it is not yet, we are at the level of the sensing. Then we need to conduct perception, and perception normally is going to represent the knowledge or to abstract knowledge from these general information. And once you have this knowledge, then you can actually conduct cognition or reasoning, and then that will help to support learning and also to support proper decision making. So that's how flexible also when you are taking the action will be related to the locomotion of the robot, both at the task level and at the relocation of the robot itself while moving from one place to the other. How to assess the action performance is also another important fact, not just to enable the robot to move, but also to assess whether the action taken by the robot is correct or not, or whether the performance is very good or less than that. And also to learn through experience. This is a very critical thing. Not to repeat same thing every time, but if the robot is making a mistake, it should make use of that to recover and adjust itself and learn from it and have a better circumstances when conducting the same task later on. How to analyze and aware about robots' current state situation, forecast or expect future events. How to interact with other human or robots, because the robot is not going to be living alone. It's always going to work either with a human nearby or with other robots. So how to interact with other robots, communicate, coordinate, including human beings. Now, the main challenge facing intelligent robotics arise from the following issues. The difficulties of the environment working in it, which is incomplete or uncertain knowledge. The environment are often dynamic, unpredictable, changing. Sensor has the limitation normally, they are not always associated with noise and always associated with a certain range. The dynamic performance also of a sensor in terms of time requirement to function is critical. So we should consider actually when you're selecting a sensor for a job to consider the limitation associated with each individual sensor. So imperfect actuators also with the mechanical structure is adding to the imperfections of the performance. The development actually try to minimize that, but there are still how to deal with them through the learning process, and the perceptual events is a critical element. Also, as to deal with real-time actions, you need to assure two things: to have proper, accurate, reliable decision-making and that's going to be realized in physical environment, is to assure that the decision being taken is correct and it's going to be done within the required time. Because having a just accurate decision is not critical, because if you have a plane that's going to crash, taking the decision what kind of problem is there is good, is needed, but it should be done before crashing. Otherwise, if the computer concluding the decision after the crashing, it will be meaningless for that decision anymore. So it is essential to couple sensing and action. And here is the extension, actually. That's why we should not limit the robot to our sensing capabilities, because we have a deficit in our sensing capabilities that the technology can actually overcome it, or the limitation that we have it in our sensing capabilities. The development of new sensors can substitute that limitation. And here, if you look at the electromagnetic spectrum, our capability is limited by this, this is normally within this wavelength of the visible spectrum. So we are actually only can see within this zone. All of the surrounding we cannot. So how to actually develop the capability to reach to all of these surrounding within the electromagnetic spectrum is here the development of new sensors is essential actually to cover that. Key issue associated with intelligence, mainly when you're talking about robot architecture as a physical structure, we should have a robust framework to support skill integration. Should be modular and distributed integration, capability to facilitate adding or removing new modules, support different level of competence, and enable effective coordination of robot sensing actions in real time. How about key software capabilities essential for intelligent robots? So here is control and execution of action, evaluate the outcome, quality of actions, navigate, avoid obstacle in real time and in dynamic environment, task decomposition, and interpret task description, requirement, goals, and target quality, motion and activity planning, extract and build representation, aware of situation, the surrounding of whether about the mission environment or people or robot around, or the danger possibly surrounding the robot itself. Learn and reason with cognition capability and apply the learned skill. Safely interact with object human. Develop tools, practices, and standards that support, accelerate, and enable better robot performance. Besides that, as I mentioned earlier, which is a hot topic nowadays to support human-robot interaction or human-machine interaction, is to have a understanding at the machine side or at the robot side, the natural language, and here you can facilitate the communication. Plus, also for a personal robot, you need to have some affection, reflection from the robot to human, and then to have a better feeling for a human when you are interacting with the robot. Cognition normally is a prerequisite of adaptability that's going to enhance performance in real time. It helps tuning perceptual process to meet the desired motor activities, because exactly it's coming between the perception and the action, the cognition. And it represents essential requirement for evolution of intelligence, and it helps use the developed knowledge. I have a book, actually, editing a book, a new book called Cognitive Robotics, which is it's open actually for contribution for those who are interested to contribute with their research activity as a chapter in this book. This is still in the early stage of the process. dealing with the human and robot autonomy. Normally, human is fully autonomous entity, but who is binding us actually from acting improperly is the responsibility. So if you are a driver, you can drive your car and hit any things. But who is stopping you from hitting these things, whether it's a wall or a human being or a shop or anything else, is the responsibility. But when you are coming to the robot, actually, such responsibility is not there. So it has a different legislation dealing with that. That's why when you are dealing with the autonomous cars, we have 5 levels, but still we are almost in the 3rd level with the difficulties in developing a legislation that allow such levels to grow to and reach to the 5th level. While the technology researcher already developed fully autonomous car, but you cannot avoid accident out of that, and hence the legislation is essential. When coming to talk about autonomy at the robot side, it is a central factor determining the effectiveness of human-machine system. Therefore, understanding robot autonomy is essential to understand human. And remember here, when you're talking about autonomy, there are 2 aspects of it. Autonomy is going to support selfishness. And when you are asking a robot to cooperate, we are going to reduce the selfishness because we need to extend help or support to the others. So it's how to balance actually between as a human being, how to balance the level of autonomy and the cooperation requirement for a certain task. And this is actually a critical issue that should be balanced. So why autonomy? Many places are not accessible by human beings, either because of oxygen, for example, not available, very high temperature, very high pressure. All of that aspects actually may affect or have a radiation that a robot cannot, that a human being cannot reach these spaces. So it needs to send a robot, and the robot should have some level of autonomy to deal with the circumstances facing it. Non-deterministic, that interaction dynamic and open environment can neither be formulated completely beforehand, nor designed or analyzed using stationary or static models. So it is a dynamic model by itself. That's why adaptive or adaptable behaviors are required in development, plus not just to pre-wire these behavior, rather than to have a dynamic, evolving behavior being established during the learning process within such an environment. Dynamic change happening as the decisions are made, because when the robot is taking action, there is a change in the environment due to that action accordingly. The environment in which the robot is living is completely a continuous and not discrete environment. And also, when you are dealing with the robot, we should not deal at the module level. A robot is a complete entity, and the modules are integrated to reflect this entity. So that's why the integration of all entities should be considered properly to reflect the final behavior or the action or the performance of the robot itself. Autonomy requires what is going to require. They require that robots not only able to control themselves, their motion based on the sensor information, but they're required to react to unexpected events, change course if necessary, capable to learn from their experience, capable to consider and coordinate multiple conflicting objectives, and able to overcome errors in perception and action. Do we need to mimic human autonomy? The answer is no, sure. Because we go back to the law of robotics, robot should obey human being without being conflicted with higher order of a law. I mean, without follow human being when asking a robot to kill another human. So when the robot is going to be out of control, then it is a human being cannot be involved anymore, because it's going to be completely autonomous and will decide by itself what it's going to do. And that is normally human being is not willing, neither humanity is actually willing to have such robots. And was a movie on that actually, I believe you remember. So technical constraints should be considered, legal and ethical constraints, information space representation, all of that would be put together. Robot autonomy and research need to develop qualitative learning, qualitative reasoning, qualitative behavioral adaptation. Robot autonomy should be bounded by ethics. Robot coherent intelligence should emerge from robot components, not all components. Yeah, I'm going to conclude.
Time is only 2 minutes left.
Yeah, I'm going to conclude. Develop effective model while interacting. Because I want just to go to this. These are the main challenges in robotic development, actually. I'm grouping it quickly. In the social interaction, we have human-robot interaction, robot-robot interaction, brain-robot, computer interface, affection. At the level of medical robots, you have higher level of autonomy, different size, scale, and purpose, micro, nano-robot, safety, because when you're dealing with medical robot, the safety is very critical and high level of consideration. Sustaining power source for any autonomous robot should sustain a power source to enable it to move without being bounded. And here is the things about power harvesting, lower power consumption, battery, better battery technology, bio-inspired and bio-hybrid robots use nature as a model, integrate and sustain living organ with the robot structure. Learning in real time, AI and machine learning supported by integrative learning techniques. Nowadays, you have the machine learning in different aspects. Perception, model-based reasoning, cognition, understanding natural language, multi-robotic agents, support cooperation, coordination, communication, real-time navigation with support of effective avoidance, mapping, cooperative mapping, localization planning, cooperative planning, robot autonomy and cognition, ethics and security, new materials, because you need to have new materials for both structure and the sensors and the actuators, control architecture, distributed, modularized, adaptable, flexible, eco design, and sustainable. Thank you very much.
Thank you very much, Professor Habib. So because of a very strict time in our conference.
Sorry for that.
No problem. This is very interesting topics. I think audience still can ask some question if they still curious about that. I would like to invite them to directly, probably next time, to message you via your email, for example. Once again,
okay.
Thank you very much for your...
Thank you very much. For those who would like to follow up questions, I will write my email.
Yes, please let the committee knows, and then we will distribute to all the
audience. Yeah, I would be glad to reply to them.
Thank you very much, Professor. And once again, we send our regards from Indonesia, from Bandung.
Thank you very much.
Safe. Thank you.
Thank you. Thank you. Take care.
Take care for you all.
Thank you very much.
At this very moment, we would like to express our deep appreciation for today's keynote speakers, Professor Katupitia and Professor Habib, for delivering us such important and insightful talks. We are very honored to have you both in Morse 2021 today. And for the moderators of the talk, thank you so much for your service. Dear all conference participants, in few moments, we are going to join the parallel sessions. For all presenters, please join the assigned breakout rooms for your preparations. And for other participants, you may join the parallel session, which are available in 2 breakout rooms. Should any technical difficulties, please kindly ask the morse 2021 help desk for your help.
All participants, we will continue our program, the parallel session, in 5 minutes. And then please take your free time for 5 minutes, and we will meet again in this room in 5 minutes, and you can directly go to any room that you want to follow. Thank you.
Test.
Terdengar, Ibu.
Good afternoon, dear all presenters and the other attendees, and welcome to the one of the morse 2021 parallel session. This is the parallel session for the mechatronics paper category. I am Triana, will be serving you as the chair session of this parallel session. And based on our schedule, there will be 6 papers presented in this session. Each turn has a maximum duration of 20 minutes. The presentation should be conducted within 15 minutes. The presentation will be followed by extra 5 minutes for the Q&A session. I will be the timekeeper and notify the presenter if his presentation duration is about to finish. Therefore, let us proceed to the first presentation. The first presentation is for the paper titled Study Sensorless Sliding Mode Control for Permanent Magnet Synchronous Motor in Solar Tuk-Tuk. Is the presenter for the paper present?
Yes, madam.
Okay. Can you talk? Oh, yeah. I cannot hear your voice clearly. Can you volume up your microphone?
Now you hear me clearly?
Yeah, it's nice.
Okay.
Okay, Miss. Okay.
Now,
Dr. Piset. Okay.
Yes. Now let me share my slide. Now we start my presentation. First of all, I would like to express my high respect to Madam Vietnam, the chair of the committee. And my name is Piset. I'm from Cambodia. Currently, I'm a master student of Department Intelligent Mechatronics of Institute of Technology of Cambodia. This is my topic that I will present today. My topic is study of sensorless sliding mode control of permanent magnet synchronometer in solar tuk-tuk. This is my content. The first introduction and the control tuk-tuk system, and the third model of the permanent magnet system, and one more sensorless control method, and one more simulation study, simulation result, and conclusion. First introduction. Nowadays, the environmental in the environment is introduction. I start from environment because nowadays our environment is not good and our overuse of the fossil let's make our environment to not good now, and want to make environment more better by technology by replace the gasoline to use electrical tuk-tuk that is the most popular in my city. Tuk-tuk is very cheap and fast, but they use all gasoline, so I want to replace them by electric tuk-tuk, and by using the sensorless, by reduce some cost of the tuk-tuk, and by using the PMSM to make operation of tuk-tuk. So that's why I choose this topic to study on the sensorless control of permanent magnet synchronous motor. For the system of the tuk-tuk, we may see the main of the system. First is the energy storage system, then called ESS. It's like a battery or capacitor or PV panel that we use to store the energy or to make energy for the electric device in the tuk-tuk. And the second one is the electric propulsion system called EPS that have a motor or another mechanical propulsion that to make the tuk-tuk moving. And my objective is to make an optimal control of the permanent magnet synchronometer. And the second one is the sensorless control. Let's make it less complex and less hardware cost. For this is my my objective that I will define. And the scope of the objective and the scope of the whole of my project is I design the control system for 1 kilowatt of PMSM, investigate the observer to estimate the rotor position and speed with effectiveness, robustness, and low cost, and develop the sliding mode control of sliding mode observer for the estimate the position and the speed over speed range. And the last is simulate with the MATLAB simulating for testing the control system. And for the mathematical model that I start from the equation of the SMO and the PMSM, that I start from this to find to make block for the MATLAB control or for the MATLAB simulating, and test it to find the with the real of the motor that we try to make with the sensor first, and one we try to replace the sensor by using the equation that we create in the MATLAB. And the first thing that I have done is make the with the simulink for the hardware, because the COVID-19 we cannot enter the lab, so we cannot testing with the real hardware, so we can finish the simulation with the MATLAB from the equation. And for the sensorless control, we choose sliding mode observer, because the sliding mode observers that we design allow the equation, model, and SMO for the estimate of the speed and the position. And the method that we find the speed and position of the PMSM, it's there are many ways that we can find, but we choose this one for the better way to find the speed and position. And we start from the voltage input, and we create a block for the PMSM and the observer by using the sine function for filter of the system, and to estimate the rotor position and speed by equation that I showed in the previous equation, and we get the feedback to find the correctness of our estimation. And this is the function. This is the block that I designed for my my observer, and we and this is the system of my research, that I have one input for my system for omega stand for the speed of the rotor that input, and we transform it to the to ABC frame for our motor, that we convert to, that we use this three ABC frame to our current controller, that convert to like PWM to inverter, and then inverter before use with the PMSM, and we use the feedback for the motor that we define with the PID, and lastly we design the observer for replace the sensor of our system that we define SMO observer that I show in the previous slide, and use the feedback of the speed to feedback with our reference speed, and try to find the error of the speed that we input and output our estimate. So this is my speed. My system, the whole system of my PMSM control system, and we also install it in our lab, but during COVID pandemic we cannot enter the lab, so we cannot test with a real experiment. And but if we use this motor for my experiment for our tok that we use with solar, and this is the result of my research for simulation result. Firstly, I use it for I test it with the very speed that start from 50 radian to 250 radian per second. So we can see that the red one is the estimate speed that we estimate from our observer, and the blue one is the actual speed that we get, and this is the green one is the reference speed that we input. So we can see that our estimate can working correctly with our input, so it's tracking perfectly. And the second one we try to use with the load, and when in this case we use the stable speed for the 250 radian per second for our meter, and at the 0.5 second we input the load for Newton met, and we can see that when we input
I think Dr. Tok got some technical problem. Dr. Tok. Okay, I think I will proceed if Dr. Tok. Yes, Dr. Tok. Yeah, Dr. Tok is not in the room right now, and therefore, unfortunately, we should skip the Q&A, and we proceed for the second paper presentation. Okay. For the second paper, the title is Self-Check in Access Control Kiosk with Automatic Card Dispensing and Storage System. Oh, Dr. Tok said. Dr. Tok. Oh, Dr. Tok. Okay. Okay. We just proceed with the next presentation. I have Dr. Leonard Trusley already here.
Hello.
Dr. Leonard, the stage is.
Thank you for the time.
I cannot hear your voice.
Can you hear my voice now?
Still no.
Hello?
Yeah.
Okay. Sorry about that. Thank you for the time and the opportunity to present in this conference, Brianna. My team member is here, Havret Lucius. So Havret will be presenting for our team here on self-check-in kiosk. Havret, you can go ahead and share screen and
all right,
our presentation. Thank you.
Right, everybody see my screen?
Yes.
Yes. All right.
Yes.
So without further ado, I would like to begin my presentation. So for today, esteemed guests, thank you for participating. I will present our project, Self-Check-In Access Control Kiosk with Automated Card Dispensing and Storage System. This project is led by Dr. Leonard Rusley, and run by me, Havret Lucius, of Swiss German University's Faculty of Engineering and Information Technology. So how did it all started? So the background is, we see a problem. We see a problem that office buildings in Indonesia still use traditional method of card exchanging, which is by using a receptionist or probably a security guard. You can see this common in government buildings, in office towers, in complex where you live. Yeah, and this is not only a time-consuming thing where sometimes security guards or receptionists have to go through hundreds of cards just to find your card. So it's time-consuming and it has a human factor which causes lower security. And of course, it's not unlike a robot, it doesn't work 24/7. And of course, humans have limited memory. So yeah, by implementing automation, we plan to change this system, which is, we hope to implement automation to the system. I know what you're thinking, but automation does not steal human jobs, but replace humans' menial task. I'm sorry, okay. Base problem. So when we started this project, we have the most underlying problems are the uniqueness of this project lies on retrieving and storing mechanism, because most card storage systems are dispensing only. inventory system back and forth. So like ATM machines, MRT tickets, it's a one-time thing. You put in your card, you get out your card. So it's not storing or dispensing. And but this system requires an inventory system. You need to store and then you return your card. So back and forth. Of course, the key factor is identification. We identify whose card belongs to who, so that we don't replace, let's say, Ms. Triana's card to Mr. Leonard's card, right? Most system does not require to identify data. For example, your ATM cards are not identifiable. It's only the chip that's being read. And of course, fully automation. Conventional building access security is volatile. That's what I meant by human intervention. Because human intervention, you have feelings and emotions involved. So with this system, by implementing this automated system, data is stored in the cloud and can be tracked, right? So the objectives of this project is to construct a reliable mechanical design for storing and dispensing mechanism, a prototype of card storing and dispensing mechanism, identification of cards with optical character recognition, and record and log information of guests that access the machine, timestamp, and assign the access cards, right? So continuing forward, this is the overall mechanical design of the 3D design of the system. We have a double decker. So on top is everything that has to do with the user, the guests. So you have the card storage, you have the solenoid housing, you have the card scanning station, and on deck we have all the electrical components required for the system. And yes, so this for the explanation, I'll dissect into two: the card scanning station and the card storage carousel. So as you can see, the card is stored from A, and then it's scanned at A, and then it's the card is stored in B in the carousel. Moving forward, we have the card scanning station design. This consists of 6 modular 3D printed cards, and the main purpose, the main job of this card scanning station is to feed the card into the system. But before it enters, it has to scan the cards prior to storage, so that we have the data we need to read the card. So we have a chamfer, so that when inside, I'll explain further, continuing forward. So this is what it looks like in real life. It's 3D printed, and it's 6. Why is it 6 modular pieces? It's because it allows it allows access to easy installation. Okay, so you don't have to have one piece that's fixed and you can't do really much about it. Yeah, so it's easier to manufacture and easier to install. Okay, for the card storage carousel, our card storage carousel can store, on this design, on this project, we built a 50 card storage. So we, for development of this project, can increase the amount of slots the cards can be stored. So we have a Lazy Susan as a base support, and then a 2mm acrylic and 1mm metal sheet as the base to just align cards, and separate extrusion support for a 3mm acrylic, so that the card just don't tilt more than 3 degrees for the solenoid to push. Why not just build an entire acrylic piece, right? If you ask, so it's because of weight. Yeah, to reduce weight and for access of installation. So this is the top view of the card storage carousel design. We have a slot mechanism, so to ensure that the top and the bottom acrylic pieces are perfectly aligned. And on top of the bottom acrylic, we have a metal sheet for the support of the cards. Why metal? Because it's slippery. It's nice for the card. It doesn't corrode. It doesn't break easily. It's durable. It's durable and slippery. All right. For the card storage mechanism assembly, as you can see on the left, the blue painted piece is the metal sheet, and then on the right you can see a home positioning sensor, a limit switch, just to make sure that the card is always the carousel is always at position 0. And we have 6 fasteners throughout the card storage mechanisms to ensure that top and bottom are always perfectly aligned. All right, for the full assembly, you can see this. So we have the solenoid housing on the left, and the card alignment mechanism is just enough so that the card just are kissed by the card alignment mechanism. And then we have the camera and camera stand on the perpendicular to the card scanning system, right? Take a look, because continuing on is all technicals and no more beauty of this mechanicals, guys, right? Okay, continuing forward, the electrical components for this project, we use Raspberry Pi, 1-stepper motor, 1 DC motor for the scanning, for the to just feed the card inside. The stepper motor is to ensure perfect positioning for the carousel system. And we have 3 micro limit switches to ensure the position 0, and then the card in the card scanning station. And then we have a solenoid to push the cards forward and backwards, forwards, 1 USB camera, and 1 power supply. All right, so this is the wiring result, as you can see, for the first base. Okay, it's pretty neat. I might add, yeah. And this is the electrical grid for the overall project. All right, and the programs that I implement in the system is SQL, for MariaDB, and PHP MyAdmin for the database. Python is the main programming language, OpenCV and Tesseract for the optical character recognition engine, right? So the sequence is like this. We have three main systems. We have homing procedure, just to ensure that the carousel is always at point 0. We have the cart insertion sequence, right? And then we have the cart exit sequence. Okay. Why do I separate this sequence into 3? Why do we separate this sequence into 3? It's because we implement this object-oriented programming, which is the class can be defined as a template that describes the functions, the objects of its type support. So after one class ends, calling out the next class, calling out the next class, calling out the next class, and in result, it's all becomes a function. Yeah, beginning with defining the class name and ends with calling out the next variable. Okay. For the database, we have 3. We have cards in slot. Now the purpose of cards in slot is to have the index number, the name of the cards. So in this case, we focus on Swiss German University's student ID, and then the slot number, and then we have the photo logging for the image, and then the access card name. So for example, Ms. Riano, our remaining guest, will insert your KTP or your student ID, and then you get access card, let's say A4, right? And then the access card link will be to that card itself. And for on the bottom, we have data lists, which will track every members or guests that enter the building. So once you borrow an access card, it's time logged, it's time stamped, so it's really accurate. You can't lie through the system. So, and then we have the slot, which just provides the data to the stepper motor of how many steps it has to move. Okay, I will now show you a video of just to get a real image of the demonstration. Okay. So in this system, we have the homing mechanism, homing procedure. So we have to align everything to base 0.0. Okay. Now this is the big thing, guys. Card insert will be driven by the feeding system into the card scan station. As you can see, it's driven in. Now the card scan station captures an image and is processed by the OCR engine, right? The card ID information will be uploaded to the database and linked to the assigned access card, which is A1 for this instance, because A1 is not borrowed yet. So, and the storage will rotate to the index position, delivering the assigned access card. So the solenoid just pushed the card, as you can see. Now A1 is out, right? Now the carousel will return to the home index position. A1 is out from the system, right? Now following out with the this is now just checking in the database. Okay, so we have the student ID inserted in the name. We have the photo for the directory of the proof, and then sorry, I'll just skip back a bit. We have the access card link, which is the access card number. Now we have the slot number and the pulse now turned to empty, from empty to filled, right? And then the access card is now filled to empty.
Excuse me,
from the access card,
excuse me, you have 2 minutes left.
oh, okay.
Yes.
So yeah, the same system, vice versa, and yep. Overall, you understand how the system works. It's pretty straightforward. I'll just run through the slides. All right. So the program, this is what the optical character recognition system looks like. So we have the program finding 1-1 and every number after that, because the common denominator for a student access ID is 1-1. So for this project, we use 1-1. And as you can see in the Tesseract process on image, you have the student ID displayed on the bottom right. And then for the card access, this is the internal storage. Because we haven't implemented the cloud system, we for now using internal storage. So we also did some test and trial runs on foreign language such as German, and as you can see, the optical character recognition did deliver and read some noise, but overall it has a 80% accuracy for the data extraction. Now for the tests, we did 5 tests with external light in the lit room and 5 tests with external light, and results came in with the external light is placed perpendicular to the card scanning station. And how did we determine the results to be valid is that if the A1 card shows A1 and the student ID shows the exact student ID. So the testing on student ID, we did 10 tests without external light and 10 tests with external light. Without external light, there's a percentage of failure of 20%, and with external light is 0%, so it's perfect. And on access card, we did 10 tests, just the same test, and without external light, we have 40% percentage of failure, and with external light, 0%. And these factors are due to dirt and reflection, and these are simulating real life problems of the cards in hand. So for the simulation test, we have 5 times sequence in and 5 times sequence out. And for each test, without the external light, we have a failure rate of 40%, and all failure are due to optical character recognition of access card, as you can see in the bottom right. And for the simulation test with external light, we ran 10 tests, and the failure rate is 0%, which gives us a reliable test. So as for future reference, this test definitely can be implemented into. It is a successful proof of concept and can be further developed for commercialization. It definitely require a better packaging right? So that the user just don't take the cards from the outside. Okay.
Thank you.
Okay, thank you so
Thank
much
you
for listening.
for interesting
Yep.
presentation, and
Yep.
system is very useful. So, is there any questions for this presentation? Oh, sure, Dr. Pansarte.
Sorry, I can't hear you. Sir. I can hear you very slightly though. Yeah, I think your mic's not on.
The volume is very small.
Yeah.
Because maybe I can help you with the. Okay. How about the problem? The quality of the card is not really good.
Right. So, sir, do you wanna take over, Mr. Leo, or?
No, go ahead.
Okay. So we did some tests, as you can see. So the cards that are dirty and that are very butak, if you can in Indonesian, very butak, yeah.
Yeah.
And
They're scratched like artifact.
real, yeah. So to bypass this problem, implementing a high resolution camera would be the solution. And for sure, for OCR, for data logging, the less data we need or the less data extracted would be better. But for sure, in a card, there's so much information and so much dirt. Dirt can be considered noise from the optical character recognition. So I mean, the best we can do is implementing a high quality camera, a 4K camera resolution, and securing our OCR coding for sure.
Yeah, OCR also has threshold that we can tune. So I believe testing different smudges of the card and optimizing the threshold so we can accept some tolerance of noise. So what is acceptable and what is not needs to be optimized.
Okay, thank you for Dr. Havret and Leonard. Is there any question? But first, Dr. Bagus, is it enough? Okay. Is there any questions? Okay, from Hidayat.
Okay.
Good afternoon, Dr. Havret. My name is Muhammad Hidayat. I want to ask you about during this pandemic, some shopping place require visitors to be having vaccinated and or have a negative COVID-19 status. Will this system be integrated in the future with information about the vaccination or the health status of the visitor themselves, so that there are no long some quickness and make it easier to if something unexpected happens? Thank you.
You have like 1 minute to answer the questions.
Yes, definitely there is something we can do to integrate. That is a great suggestion actually in the light of COVID-19. This system was originally developed before the pandemic. So now I think that is an even greater purpose and function. Thank you.
Thank you so much for Dr.
Thank you, Mr. Leonard and Dr. Havret.
Yes, thank you so much for the presentation and good discussion. Now we will proceed to the third presentation for the
Thank you all.
paper titled Traffic Flow Estimation Using Cloud-Based Traffic Velocities for In-Vehicles Application. Is the presenter present? Oh yeah, Dr. Lucas is here. Okay. Okay, Dr. Lucas, take your time.
Hello, Lucas Bennett speaking. Can you hear me? And are my slides visible?
Yes, it's clear and your slide is already seen.
Perfect. Then good afternoon, everyone. Unfortunately, we cannot meet in person today, but nevertheless, I'm very pleased to present some of my current research results within the mechanics session of the Morse conference today. And I'm a PhD student at the Institute for System Dynamics at the University of Stuttgart, Germany. And at our institute, we take a look at different applications of engineering with the systems and mechanical point of view. And I'm working in the field of advanced driving strategies, and today I would like to present some results of traffic flow estimation using cloud-based traffic velocities. First of all, why is it important and interesting? First of all, there's an increasing amount of traffic participants on highways that provide live traffic data of their own behavior. And there are some kind of navigation service providers, such as Google here or TomTom, which collect this crowd data and then aggregate into a better traffic velocity estimate. And this estimate is available via own APIs and can be requested by individual vehicle participants on a highway, for example. Another point is that the current traffic situation strongly influences the vehicle behavior, which means, for example, if one vehicle has a predictive cruise controller that adjusts the velocity choice according to curves or speed limit changes, then this predictive planning is always influenced by the current traffic situation. And if it's possible to estimate that traffic situation with a model-based representation of state behavior of the traffic, which enables an adaptive and forward-looking planning of the own vehicle behavior, and this leads to an improved energy or driving management. Within the talk today, I would like to start with a short introduction of traffic flow modeling, describing the model equations and the discretization scheme. Afterwards, I would like to show the traffic flow estimation setup, where I'm going to show the measurement vector, which allows for the application to online available velocity measurements. Then I will show the extended Cannon filter setup, which performs the estimation. Afterwards, I will go on with the application setup and show the available cloud data, and then show a simulation scenario, which I use to test the performance of the estimation setup. And finally, I will show some simulation results. So first of all, traffic flow modeling, there are typically two approaches. One is a microscopic approach, which simulates all individual vehicle behaviors. And this is typically quite handsome and difficult to parameterize because you need information about each individual vehicle on a highway, which is normally not available. Therefore, a macroscopic approach is used more often, which is based on partial differential equations. And they contain two traffic states, namely traffic density, which describes the amount of vehicles within a certain highway stretch, which means position, and then traffic velocity, as I already mentioned, in speed. And furthermore, there's a measure called traffic flow, which can be calculated out of the two aforementioned ones, and describes how many vehicles are passing one position within a certain amount of time. And beyond those model equations, and the first equation is the important one, the continuity equation, which states that the amount of vehicles within a segment changes with the amount of vehicles going into that segment minus the amount of vehicles going out of that segment. And then we receive this partial differential equation depending on position and time. And furthermore, change of velocity is described by an acceleration equation. And this consists of three terms. One is the convection term that simply describes the propagation of the velocity profile. Then there's an additional relaxation term that describes a damped adaptation of the velocity towards the current traffic density. And this is a very important relation in traffic flow modelings. And on the next slide, I will go into further detail onto this. And the third term is the anticipation term, which describes some kind of predictive adaptation towards density changes. So as I already mentioned, the function V of density describes a relationship that states how fast can vehicles go depending on the current traffic density. It is called the so-called fundamental diagram, which consists of three parameters and is shown on the right plot in the bottom, where you can see that one parameter is the free flow velocity that describes how fast can vehicles go if there's almost no other vehicle on the road, so the free flow case. Then there's a critical density when velocity starts to decrease due to increasing density. And furthermore, there's a shape parameter A, which describes how steep this change is going to take place. And as it is shown in this plot, this curve is being identified from real measurement data, which is also plotted in gray. And the takeaway message from this plot is that the higher the density on a highway is, the lower the velocity is going to be possible on this highway. Now I would like to show the discretization scheme for the implementation. And therefore the highway stretch is divided into n segments with a length of 100 meters in this case. So the continuity equation turns into an ordinary differential equation for each discretized position. And so we've got two equations for each segment, one for the density change and one for the velocity change. In order to put those equations into a state space formulation that can be used for an estimation setup, a state space representation is chosen of the discretized model, which contains all the density states for all positions from 0 to n, and all the velocity states in addition. So all the states are represented here. And then we've got the dynamics equation, which consists of all the individual and discretized functions which have been derived before. Furthermore, there's a noise added to the process, which is going to be considered in the extended Cannon filter setup later on. Now, the important point concerning the measurement of online available cloud velocity information. So we have to define a measurement equation that describes the output of our system, and this one contains only the velocity information over the complete position, which means that we assume that we can request the velocity of a certain highway stretch from a cloud service and include it into our measurement setup. Additionally, there's an uncertainty or noise process with covariance matrix R. Then a typical extended Kalman filter is designed, where we've got in the first step the time update of the estimated state and the covariance according to the model equations F. And in the second step, the measurement update is being performed of the estimated state as well as the covariance. And this can be done every time that a new measurement or new request from the cloud velocity data is available. And if no update measurement is available, the data is being used. Why is this relevant? Because later on, I'm going to show that the online traffic velocity information is not requested frequently, but with an update rate of approximately 30 seconds. And furthermore, there are the Jacobian matrices as shown here. So let's take a look at the application setup. This is an example request from the cloud service provider here, where we are using the routing API. And this provides a traffic speed value for a requested route, and exemplary in this plot with a highway stretch of 30 kilometers. And we can see that the blue line shows the current traffic velocity, so the traffic speed on this highway. And additionally, there's information about the base speed, which describes some form of expected velocity on the highway, depending on historical data. So this does not include live traffic data. And as we see from this plot, especially at 15 kilometers and after 20 kilometers, we've got a lower traffic speed. So in this case, we would have some kind of traffic jam or condensed traffic situation. As we can see, those segments are piecewise constant, which means that we've got discretized position segments, which are variable in length. So this has to be considered when applying this online traffic speed into an estimation algorithm. Therefore, I analyzed the length of the segments and the occurrence. So mostly the segments are quite small and around 50 meters long, but sometimes they're even 500 meters long or up to 1 kilometer long. So this is going to be considered in the following estimation setup. Furthermore, the traffic velocity that is being provided by the online service is not always accurate. So there's an unknown offset to the real traffic speed. And the traffic data is also updated every 30 seconds, as I mentioned before. And for this study, I defined a simulation scenario where a traffic jam appears with a velocity drop from 80 kilometers per hour down to 20 kilometers per hour, as shown in the right plot on the bottom. And for this velocity profile, chosen as an initial condition, I defined random measurements as it could have been provided by an online service. With the gray lines, so we've got variable segment lengths and an unknown offset to the real traffic speed. And this scenario is simulated with the before and introduced traffic flow model. So we can see the initial condition with fast velocities and then slow velocities, which are going to change over time. So the traffic jam is going to move forward in position and is disappearing after approximately 300 seconds. Additionally, we can see the density, which behaves inverse. So first we've got a low density and then an increasing density due to the slow velocities. And then traffic jam is disappearing and we're having normal densities again. If we apply the estimation setup to this scenario, then we can see the estimation error in those two plots for the velocity on the left side and for the density on the right side. And first of all, the 30 seconds intervals are visible. So every 30 seconds, there's a new measurement update. And then the traffic speed as well as the traffic density is estimated from the randomly generated measurement. So those two plots only show one specific case. And since we've got a randomly generated measurement, the study has been repeated for 100 times. So we've got 100 iterations with randomly created measurements. And in those two plots, we can see the root mean squared error once plotted over time. So the average over all states. And we can see that the average is quite small in density. Sometimes if there are small offsets in the measurements, there are also larger errors, but the mean over all 100 iterations still keeps very small and below 5 kilometers per hour. The same is observable if the root mean squared error is calculated for the spatially distributed states. So over precision, we can see that especially at the end of the highway stretch where we've got a lot of change, the error sometimes is bigger, but the mean is still quite low. And the overall estimation error is 2.31 kilometers per hour and 3.8 vehicles per kilometer in density, which is a quite small value if we consider the variable segment length and the offsets. This already leads to my last slide, where I would like to conclude that a partial differential equation traffic flow model simulation has been shown and an estimation setup was established that is able to reconstruct traffic states using only velocity information that is available online by navigation test riders. And this has been tested for an exemplary scenario with a typical traffic jam situation, which led to very small root mean squared errors for velocity and density. Next steps are going to include the application of this tested algorithm to real traffic scenarios, and therefore a measurement and a validation test drive is necessary, because if we want to validate the estimation of real traffic requests, then we also need some validation data of own vehicles driving on the highway at the same time. And furthermore, with the estimated states, model predictions shall be performed in order to predict the upcoming traffic situation over time. This is the end of my presentation, and I'm looking forward to remarks or questions, and thank you very much for your attention.
Thank you. Nice timing. Thank you, Dr. Lucas. Okay, now we continue for the Q&A. Is there any questions?
I have asked you one question.
Sure, Dr. Bagus.
I hope. Just one moment, there's a little bit problem with the feedback. So just now you said about updating the information about every 30 seconds, right?
Yes.
So updating information, according to me, depends a lot on the speed of the vehicle, right? So if you have slow speed, so you may reduce 30 seconds. But if the velocity is quite high, is that not too long to update the information? Would you explain about that?
Even if we take a look at 2 kilometers and then the update rate. So the problem is that the online services only update the information every 30 to 60 seconds. So there's no sense in repressing it more often, because then we only see the old data that has already been available before. And if we take a look at the scenario in this case of 2 kilometers, then we take approximately 90 to 100 seconds to pass through this segment. So we've got 3 requests within this time, and this is typically enough to see a change in traffic velocity early enough to react to it.
Okay, thank you.
We still have some time. Is there any questions for Dr. Lucas? Okay, thank you, Dr. Lucas, for your presentation. Now we proceed for the fourth presentation. The title is Prototype of a Multi-Story Motorcycle Parking Garage. Dr. Bagus.
Hello. Good afternoon, everyone.
Yes, Dr. Bagus. You may proceed to present.
Just a moment. Okay, hope we can see my presentation. Is it already shown in your screen? It's already presented. Okay.
Yes.
So I would like to talk about the prototype of multi-story motorcycle parking garage. So in Indonesia, the population is growing quite high, and especially transportation is really important. And motorcycle is the most populated vehicle in our society. Motorcycles is an affordable vehicle for our people in Indonesia. So when you come to a certain place, you are a bit difficult to find available parking space. So required parking area need to be increased, because parking lot is right now is insufficient and difficult to find. And this also, if we cannot have a good enough parking space, So it will lead also to reduction in the street. Coefficient parking is not a good solution. It's an effective solution right now because construction and maintenance costs are not cheap, also considerably less safe. Instead, risk of being hit by a car, loss, and also slow. So we try to have look to another solution, for example, multi-story parking system, and it is a suitable solution for smart parking because it's responsive to user and it is a bit cheaper, actually safer than conventional system, and can be automatically operated, and some other features offered by the automatic parking system. For example, here we see in Japan they have a very high parking system, a 3-level here, and for example, of course, you need a certain algorithm how to take out the car or retrieve a car from a certain place because it could be it is avoided to get out from the car. And we also have seen in Germany, I think, a lot of multi-story around like a cylinder form like this. So some places in Japan, I think they already developed a very huge parking place under the ground. And once again, you need a certain algorithm how to easily retrieve a car which parked very far from the entrance point. But all the examples are for car parking. How about motorcycle? There are very few research demonstrating this kind of problem. For example, Setish designed a bicycle impala, and Sunny designed motorcycle parking place for motorcycle, but it's limited only for frame analysis. For example, this is from Sati. It's they still have only for bicycle. Sorry, prototype. It's not implemented yet, but this is good for our case. They have designed a multi-story parking place for motorcycle, but they mainly consider only the analysis of the frame, not the total system we call an automatic parking or smart parking. And in this work, we try to design a parking place, automatic parking with 2-level, and for example, kind like this, so design in a real size, and we design 2-level parking system, which in each level we make an example of 3 slots. So we have totally 6 slots. And this work mainly focuses on designing the mechanical system and also designing the mechanism how to clamp the motorcycle to be inserted or to be parked and retrieved from the system, from the parking place safely. And then to also design a mechanism or algorithm how user can, for example, want to park the motorcycle and at a certain time they want to retrieve it at any time. So we make a prototype of this system and we produce manufacturing analogy. So we design it almost exactly the same as our mechanical design. So this design can be resized according to user requirement. So for example, you want to make 10 level down there of let's say 10. So every level it is still possible, very easy to extend it. The main concern should be the dimension of the sticker crane. So as the higher the sticker crane, you have to think about the stiffness, the strength, and also especially the column, because if you have very high column, there will be a problem with buckling. So we have to be really considerate about the sticker crane design. Okay, just I said, just now design was live only for set load. All the members and prototype is made to visualize the principle of the system. The prototype was made using 3D printing. Experimental work to carry out to examine the algorithm developed to manage the storing and the retrieving of the object, in this case is the motorcycle, the miniature of motorcycle. Experimental work were also carried out to check the functionality of all actuators and sensors used in this prototype. And the algorithm developed in this system, we start with, let's say, showing a terminal for the user. There's a button, button, and retrieving button. So user come to the front of this panel. So the system will work continuously to check is there any motorcycle coming in front of this panel. So if there's one person coming here and they press the parking button, for example, the system will check whether this is task to retrieve or parking. Of course, in this case, to the right side of the flowchart here, it will park the motorcycle, and the system will check whether they come just 1 hour before the closing. If it's only, let's say half an hour. So the closing very soon, so they would be accepted here. And then if it's still long way to the closing point in the morning, so if it is full, there's no capacity, so it's also rejected. So the motorcycle also rejected. If the capacity is still there, so the parking action is taken. And then after the motorcycle is parked, of course, there need to be the number of the motorcycle side need to be treated, as well as for retrieving action. If somebody retrieve one motorcycle, of course, there is no rejection. So just motorcycle from the place, and then the number of the motorcycles should be updated again. So let's make it simple. We have a main algorithm, parking and retrieving. Because here, when parking, after ready with all this procedure, and the front wheel will be clamped. After that, the body will be clamped, and then the sticker will come to the entrance, and then take the motorcycle inside to a certain place, which is assigned by the system. In this case, in this example, we assigned by ourselves, just for simulation. But for the rest of the system, there should be one algorithm, one module that has to determine which is the closest point from the entrance. So we try to optimize or to minimize the energy that we need to place the motorcycle in the system. As well as the retrieving, of course, the retrieving there's no problem because we know the position of after, of course, the user showing the ticket from the panel, and since we will input the number of place where the motorcycle was parked, and then the train will go to that place, then sticker will go inside and clamp the front wheel and the back wheel. Of course, when I just forgot about saying the parking, when the motorcycle has already parked, now the parking place inside the system will clamp the wheel and the front wheel as well. So the system works the flow very simple, and then the uses Arduino Mega to monitor the input or input from, for example, the detecting of arrival, or the starting button, the keypad in this case to represent the scanning action, and then they already have their own motorcycle back and they want to get out. And we need output from Arduino to, for example, say what's going on, activating clamping for front and rear wheel, and activating sticker go to service. Okay, let's say we represent the algorithm using very simple electronics. If the capacity is there, so there's some empty space, so the system will say there will be positioning system, and you can start. If the capacity is not there or the parking is full, so you will see the display mentioning that the parking is full. If it's okay, so you see the motorcycle will come first in front, and then there is a kind of detect mechanism to take in the motorcycle. After that, of course, we need to clamp the body first. Because, let's say you have a motorcycle in vertical position, so you need to have at least one clamp in front and two clamp on the back side. So it will make the position of motorcycle steady during the parking process. And then after clamping all the important point, the sticker will take the motorcycle to sticker to inside the sticker, and it will bring it to a certain position that is designed. In this case, we designed it manually, but for the future, we will generate algorithm to see where is the closest parking place from the entrance right now, because the closest position could be vary every time. Okay, it's not fixed. And you see here, motorcycle, the is already parked inside the slot. Of course, with clamping action, clamping mechanism as well in this case. So that's the parking. How about retrieving? So in retrieving, you input the number where the motor is parked. In this case, actually, because we did it manually, so we know where it's parked. But in the real situation, we'll have a ticket. There is a barcode mentioning where is your motorcycle was parked actually. Okay, and then you just press start, and then here the sticker print will go to the target wherever the motorcycle is, and then of course the sticker will bring the fork going inside of the motorcycle, clamp all the important point, and then after making sure that all the mechanism works, and then the sticker will take out the motorcycle and bring it back to the entrance point. Then this makes sure that the user will should sit on the motorcycle, and then after that the clamping may release. Otherwise, the motorcycle will fall down. But it is still in the not implemented yet. Okay, so to improve the system, I saw a method in Japan that for bicycle parking they have almost similar system. They clamp the front wheel, but of course not clamping the back side because it's very light. So they put a RFID tag. So we will use the same way, and we need to integrate the gadget of user. So automatically they can take out whatever they want, integrated with a payment agent, for example, provide with optimizing criteria for close scalable load, just like what I said just now.
So let's say, because time is only 1 minute left, let's make a conclusion. This is a really simple system, but quite become a solution for our problem now. We can make a model, 3D printing technology. The parking design was only for accepting motorcycle, and then it's only for 2 level 3 parking lots. And then it's already proof that motorcycle park and at the point where it's assigned. So I think that's all for my presentation. I hope this work will give you idea. And of course, there's still what's that in accuracy, so we need to improve it in the future. Thank you very much.
Thank you, Dr. Bagus. Your presentation would be very useful to save places in the crowd cities. Now, is there any questions for Bagus research? Okay. Okay. Thank
We
you
go
very
to the
much.
next.
Good afternoon, Dr. Bagus.
Oh, Fatan Hidayat.
Can you hear me, Doctor?
Yes, we can hear you.
I want to ask about this vertical parking. In the process of waste,
could you please repeat once again? Sorry, Fatan.
Can you hear me, sir?
Yes.
In the process of inputting and removing the clamp, and also inserting or removing the motorcycle in the slot occurs automatically. So, what are the steps to be taken if the power supply used in the parking lot goes out, and are the clamps are safe in case of force opening or in the event of an earthquake or other shock, and whether these clamps can adapt to a variety of fields. Thank you, Mr. Bagus.
Oh, this is really difficult question from Fatan. Okay, the view, of course, this is real problem because we have underground parking. So we normally have emergency genset. Okay, so of course you need emergency genset, of course. Otherwise you cannot work for that. And earthquake, I just think about try to design the mechanical system as strong as possible. Okay, that's the only I can say. And also about the clamping, if you lost power, there is a special rules in designing clamping. So you have what we call it action clamp. Two action toggle clamp. So you need to really think about which is the action to clamp, because both direction has different forces. So you have to use smaller force for clamping and higher force for unclamping. So in case you have lost power, you can still release it. Otherwise, you cannot do anything. So there is a rule in clamping mechanism. I think that for now, that's all I can answer your question. Okay.
Thank you, Dr. Bagus.
Thank you, Dr. Bagus. Now we should proceed for the fifth presentation. The title is Sensor Placement for Qualitative Fault Diagnosability in Large-Scale Adaptive Structure. The presenter is already.
I hope you can hear me all right, and also see my slides.
Yes, it's okay.
Okay, very good. Then I think we can start. Hello, everyone, and now welcome to this talk on sensor placement for qualitative fault diagnosability in large-scale adaptive structures. My name is Jonas Stiefelmeier, and I'm a PhD student at the Institute of System Dynamics in Stuttgart. And now, before we dive into the details, I'd like to briefly motivate and introduce the concept of adaptive buildings. So the construction sector is responsible for around half the global resource consumption and additionally about 35% of the emitted greenhouse gases. So considering our urgent problems of climate change and the scarcity of resources, as well as the steadily growing human population, we somehow need to change the way in which we build in order to lower these numbers. Now I'd like to zoom in a little from the construction sector as a whole onto high-rise buildings specifically, because these require particularly much material in order to achieve the required stiffness so they can withstand loads, for example, due to wind. Now, if we just simply reduce the cross-sectional area of our building, then we'd get unacceptably large deformations and also make the building prone to vibrations. But instead of just using more material for passively increasing the building's stiffness, we could alternatively also just counteract those loads actively using, for example, hydraulic actuators, as indicated by these blue arrows. And then these forces provided by those actuators can be adapted dynamically, so also allowing them to dampen oscillations occurring in the building. And in that way, the resource consumption and thereby also the CO2 emissions. Now, to investigate the validity of this concept a little more closely, and not only in theory, a test building has recently been constructed at the campus of the University of Stuttgart, as you can see here in this image. So that's a 36-meter high test tower. And below the white facade, which is by now hiding the most important parts of the building, there's this steel structure with hydraulic actuators incorporated into some of the elements. Now, for actively compensating the effect of external forces, we of course also need various sensors. Let me just display the pointer for estimating the system state, and then the controller can use this estimated state to determine the forces that the actuators have to provide. Now, given this large number of actuators and sensors and the long time over which such a building should be used, it's to be expected that at some point at least one of the sensors or actuators will fail, meaning that it stops working as intended. Such a failure would then directly influence the control loop and might therefore be quite uncomfortable for the inhabitants. And therefore, faults in the actuators and sensors must be diagnosed promptly and reliably so that appropriate countermeasures can be taken. That means that faults must first be detected, so meaning that we decide if there's a fault or if there's no fault. And in addition to that, they must be isolated or localized, determining which of the sensors or actuators is the faulty one. If and how reliably faults can be detected at all, of course, depends on the available sensors. That's what the term fault diagnosability means. Now, in this test building, we have a total of 48 strain gauges and 32 optically measured points. So we have quite redundant measurements, which is exactly what we need for fault diagnosis. In the future, however, those buildings should not contain unnecessarily many sensors. But of course, on the other hand, it must not become apparent during operation that we cannot detect faults in some of the sensors or actuators. So our objective in this paper was to ensure prior to operation of the building, and ideally even prior to its construction, that the planned sensor system allows for a sufficiently reliable fault diagnosis. And if that's not the case, then we want to extend the planned sensor system suitably. In the following, I'll now show the results of a qualitative analysis, which is a technique for determining which faults are diagnosable in principle. And then based on the results of that analysis, we can optimize the placement of sensors, meaning that we choose a subset of sensors from a larger set of possible sensors that we defined earlier. This qualitative diagnosability technique is based on the concept of the parity space, which has been studied quite a lot in the fault diagnosis community. In the approach, we start with a linear discrete time state space model, as shown here, and we accumulate the measurements over several time steps, resulting in this sort of sliding window model. And then by filtering the measured quantities y and u in a suitable way, we get to the so-called parity equations, which are shown down here. Specifically, that means by multiplying the measurements from the left with a basis of the null space of these matrices R and H, we can eliminate the influence of the unknown states and unknown disturbances, which leaves us only with the influence of the vector f. However, for these equations to be meaningful in any way, this null space must of course not be empty, and also the product of this null space with Q must not be empty, right? So it must not be the zero matrix. And then based on this, we can analyze the diagnosability of faults. We then call a fault detectable if the image space of its input vector is not contained in the image space of R and H, because only then does this left multiplication with the null space of R and H not result in an all zero vector. So only then can our fault still influence the filtered measurement here on the left-hand side. Similar criterion can then also be derived for the pairwise isolability of faults, where we just simply have to extend the right-hand side for the input vector of the second fault. To evaluate these criteria another, I use these equivalent rank checks that you can see here, just since they are simpler to evaluate numerically. Here we have a small caveat, since we only evaluate pairs of faults for isolability. Multiple simultaneous faults can of course still have undistinguishable effects on the measurements. But in this study, we assumed that faults occur independently and only very rarely, and that after a fault occurs, it will be diagnosed very quickly. And then it's reasonable to assume that at any one time step, we only have to diagnose a single fault. Now, in order to evaluate a whole sensor placement, the detectability and isolability of all faults in sensors and actuators has to be evaluated with the criteria that I've just shown. leading to a detectability matrix D and detectability vector D and isolability matrix I. These then contain ones where the faults are diagnosable and zeros where they're not. So for the example of test building, I executed this leading to the isolability matrix here on the right, where the yellow elements are ones and the blue elements are zeros. And here you can see that most of the faults are distinguishable from all other faults. Only here, the actuator faults, we have a few faults which cannot be distinguished. Those correspond to actuators in the columns in the first few stories, as indicated by the pairwise identically colored columns here. So for those, faults are not distinguishable among each other. Okay, now since we want to evaluate different sensor placements and compare how well they perform in fault diagnosis, we use this diagnosability as a baseline or specification indicated by the index S. Okay, then finally we can formulate an optimization problem for the sensor placement, which is set up as follows. We're searching for a subset P of all possible sensors P full with the minimal number of sensors. And these inequalities down here then constrain the sensor placement such that the corresponding system does not violate our desired fault diagnosability. In two previously published papers, researchers Chris Sandra and Frisk have assumed a sufficiently long sliding window in the model that I've shown earlier. And in that case, adding a single sensor always renders a previously undetectable fault detectable. And in that way, they can then decompose this optimization problem into a set of easily solvable subproblems. However, for our test building here and also more generally for other large-scale adaptive buildings in the future, such an approach is not feasible since for our large models, these long sliding windows lead to numerical inaccuracies, both in this diagnosability analysis as well as later for the implementation of the actual fault diagnosis. So in this paper, I therefore considered a fixed smaller window length for which feasibility can be ensured. I then tested two different approaches to solving this optimization problem. The first one is called a destructive approach. In this one, I initialized the sensor placement as the set of all possible sensors, and then iteratively, I tried to remove each sensor in the set. If removing the sensor violated the specification, and if it was not violated, then the sensor is actually removed. Then this resulting number of sensors in P is a local minimum of this optimization problem up here, as removing any other sensors would, of course, violate the specified diagnosability. In a second approach, I optimized sensor placements using a genetic algorithm. For this algorithm, I removed the inequality constraints up here, as it was difficult to enforce them throughout the mutation and recombination procedures in the genetic algorithm. And I instead introduced such a penalty term, alpha times V of P, where V of P here is the number of violations of these constraints. And if we then choose alpha sufficiently large, then we can ensure that the constraints are still satisfied at all the local minima of this cost function. Okay, so evaluating both of these approaches for the considered system, both approaches always led to sensor placements containing 14 sensors. So randomized execution led to different sensor placements, for example, iterating over the sensors in an more destructive approach, or randomly utilizing the genetic algorithm's population led to different sensor placements, but all of them contained 14 sensors. So the placement was not as important, but more the number of sensors, which I guess also makes sense intuitively. And you can see in the resulting isolability matrix on the right, the isolability was retained for all. We still have these non-distinguishable faults, which I've shown earlier, but of course, removing sensors cannot improve fault diagnosability. There were, however, no obvious patterns in how the sensors were placed, which is why I also analyzed a larger number of random placements in addition. So as all previous optimal solutions had 14 sensors, I thought it would make sense to evaluate 10,000 more placements, also with 14 sensors. And surprisingly, 69% of these random placements attained the maximal fault diagnosability. And all sensors occurred at a really similar rate in these optimal solutions with a standard deviation of only around 1%, meaning that no single sensor was chosen significantly more or less often.
Principal Mayor, you have 1 more minute.
Oh, okay. Yeah, then in order to check if specific cluster sensors preferably occur jointly or separately, I also analyzed the correlation between the sensors. However, there were also almost no statistically significant results with respect to that. I'll go over that a little more quickly now. So we could not ensure global, that our approaches find the global minimum of the optimization problem. I also checked another 10,000 placements containing 13 sensors to see if we can find better global optimum. However, none of these 10,000 placements attained the specified diagnosability. So if there exists a global optimum with this lower number of sensors, then it's much more rare than the local minima with 14 sensors. And that's most of the results already. So this diagnosability analysis that I've shown provides an a priori estimate for the performance of a fault diagnosis system, and could, of course, also be applied to other systems. Both investigated local optimal sensor placements, perspectives, criteria, and for this system of an adaptive building, the diagnosability depended mostly on the number of sensors and not so much on their placement. However, this criterion that I use here lacks guarantees for the robustness of the diagnosis or the accuracy that we can achieve. Therefore, I, in the future, want to develop a quantitative analysis which also takes this reliability into account. And then in the following months, as soon as our adaptive test building will be taken into operation, I also will validate these results on real-world measurement data. That marks the end of the talk. Thank you very much for your attention. And yeah, if you have any questions, I'll gladly try to answer them.
Thank you. Dr. Stifel-Mayer, is there any questions?
Yes, please. Yes, please.
Okay,
I've got one question. Mr. Stifel-Mayer.
Yes.
Okay, just now you said about the deflection of the building.
Yes.
If we look at from outside, we can easily see the deflection according to certain reference. How do you measure deflection when you put a sensor inside the frame itself or the structure itself? That's the first question. The second one is
sorry.
About actuator. Actuator, I think it should be two direction, right? It can be extended, also it can be retracted like that. Is that correct?
So these hydraulic actuators can only be extended, but since we have actuators in many of the different elements, we can still achieve any kind of deformation in the building. So we have redundant actuators, so only extending them still leads to a full manipulability of the building.
Yes, but if you want to try to minimize the deflection, of course you better give action here and the pull action and push action, right? To make it easier.
Yes,
because you put a lot of actuators, I saw, on every level, I think. Is that right?
Yeah, that's correct. So we have actuators both in those vertical columns as well as in the diagonals, but yeah, they can only extend due to the, since they are hydraulic actuators. Of course, it would be ideal if they could also contract, but yeah.
How about the sensor? Because how do you put that sensor? What kind of sensor do you use?
We have two main types of sensors. So one, we have strain gauges measuring the extension of our elements. So yeah, by how many percent they are extended. But in addition to that, we have cameras mounted on two sides of the building as indicators. So these provide absolute coordinate measurements. So that's quite important for observing the full system state.
Thank you.
Exactly.
Thank you.
Okay, thank you, Dr. Stifel-Mayer.
Okay, thanks for your attention.
Now we should see for the last presentation for the paper titled Evaluation of Novel Safety Concepts for Automotive Perception in Real-World Environments. I see Dr. Philip Stelzer is here. Dr. Stelzer?
Hello.
Hello.
Yes, I try to share my slides.
No, it's not shown yet. Please share your screen again. Now it's
Now,
clear.
do you see my slides?
Yes, I can see your slide. Please proceed, Dr. Stelzer.
So, but my video isn't possible to enable it. Okay, should I proceed without video?
Yes.
Okay. So, okay. At first, warm welcome to my presentation about our publication Evaluation of Novel Safety Concepts for Automotive Perception in Real-World Environments. My name is Philip Stelzer. I'm a PhD candidate at the Institute of Technical Informatics from Graz University of Technology. At first, about the agenda, which is composed as followed. At first, I will give a short overview about the Pristine project where we are contributing in. Then I will talk about the sensor fusion platform, which we have used for our novel safety concepts.
Ramadan, Ridwan, and Taufik Ashidiki from Bandung Polytechnic for Manufacturing, Indonesia. So please, Mr. Nur Jamiluddin.
Yes.
Please, the stage is yours. The time is okay.
Bismillahirrahmanirrahim. Good afternoon, ladies and gentlemen. It is an honor for me to be able to attend today as a presenter at the International Conference on Mechatronic, Robotic, and System Engineering 2021 on morse. First of all, I would like to say thank you to morse 2021 committee for giving an opportunity to present our work in this conference. Okay, let me share screen. This research is motivated by the needs of industries in the current industrial 4.0 era by implementing autonomous mobile robot, and the algorithm SLAM or simultaneous localization and mapping is very popular method to control mobile robot, and we focus on the wire-based SLAM, which is a visual-based SLAM. This research purpose is learn how wire-based SLAM 2 algorithm as a visual-based SLAM generate environment map from image data, and then to implement wire-based SLAM 2 algorithm in Robotino mobile robot with monocular camera sensor and evaluate the map result from the system and compare it with the real state of the robot environment. This is the system overview. It's simple. We use Logitech webcam series C920 monocular camera mounted and attached to the Robotino 3 mobile robot with ROS or robotic operating system installed. And then the Robotino will communicate wirelessly to the server computer. This is the hardware used. We use the Robotino. Robotino is the mobile robot platform for research and education manufactured by Festo Didactic. With its omnidirectional drive sensor, interface, and application-specific extension, Robotino can be used very flexibly. The most important programming language and system are available for programming individual application. Robotino has a bumper sensor around circumference, infrared distance sensor, a color camera with figure resolution, and many more sensors. So for signal input and output, Robotino has several interfaces like USB, Ethernet, EIC digital and EIC analog inputs, EIC digital output, additional motor output for driving high loads, additional encoder, and the power is supplied by two 12-volt 5 ampere battery. And in this study, we use Ubuntu 18.04 as the operating system and the ROS melodic. ROS is the open source robotic programming framework work in Ubuntu operating system, which is used for input and output control as well as robotic communication. The ROS system starts by initiating the computer as master, then the computer also executes the keyboard teleop node for the robot. And then the Robotino node, wire-based SLAM mono, and Robotino camera node are executed on the robot. The keyboard teleop node will send a topic or the data named CMD file. This is the command velocity to the robot via the Robotino node. The topic carries a message, command, the movement to the robot, both linear and angular movement, so that the robot can move with its camera to explore the environment. The camera is commanded by Robotino camera node so that it can send the data with topic image raw to the topic wire-based SLAM to mono. It is not the image is computed so that it becomes the data need to create a map. Like a map, point, robot position, and orientation. Image processed by algorithm and the robot trajectory. This is the picture. It's the flow diagram of the ROS system to create the map using the ORB SLAM2 algorithm. This is the system flowchart of ORB SLAM2. There are three main program or three main algorithm, which is tracking, local mapping, and loop closing. And then in the end, it will be bundled by the full bundled adjustment to update the map. As you can see, the system take the frame, the image raw from the camera, and then they process it by the tracking algorithm, and then it will get the keyframes. Keyframe is the data represent the point in the world environment. And then it will be executed by the local mapping algorithm and then the loop closing to create the map representation of the environment. In order to project the coordinate of the 3D world onto the drawing plane, we use pinhole camera model. The image is placed at distance f from O, where f is the focal length of the camera. Then it considers the point P, XP, YP, and ZP in this coordinate system. If we consider a two-dimension coordinate system in the drawing plane with the center at point R, which is the intersection of the axis of the 3D world coordinate system and the point Q, you get XQ and YQ in the drawing plane. This image shows the pinhole camera model. The R and T metric have a very important role in both visual odometry and SLAM visual system. This is the algorithm of FAST. Basically, the ORB is acronym of oriented, fast, and rotated brief. So we have two main algorithms. The first is oriented fast. Fast, or the acronym of features from accelerated and segment test algorithm run as follows. Given a pixel P in an array, and then the fast compare the brightness of P to surround 16 pixels that are in a small circle around P. Pixel in the circle is then sorted into three classes. And then the key point found by the fast give us information of the location of the remaining edge in an image. And then the fast feature do not have an orientation component and multi-scale feature. So ORB, or oriented rotated brief algorithm, use a multi-scale image pyramid. Once ORB has created a pyramid, it uses the fast algorithm to detect key point in the image. By detecting the key point at each level, ORB is effectively locating key point at a different scale. After locating key point, ORB now assign an orientation on each key point. And then brief, or acronym of binary robust independent elementary feature, take all the key points found by the fast algorithm and convert it into a binary feature vector, so that together they can represent an object. The ORB SLAM2 algorithm is implemented in the Robotinum by robot to generate map of the environment. The system is aimed to be able to detect object by projecting this object onto a map created by the system. It is the result. In its implementation, the system succeeds in building the map point to resemble the shape of the object profile. The figure shows a set of map points that form an environment object, which is a gallon of water, and then this profile has a circular base with the coordinate at the center of point 0.437, and 0.122 and minus 0.078 with a height on the z-axis 0.002 with range of minus 0.078 to 0.095. And then we also implement or try another object. This is the figure of block shape profile. And then the system successfully create the map points represent the object in the environment.
Sorry, Mr. Jamiluddin, your time is
Okay, I will.
5 minutes more.
Then we also do the measurement. Previously, this measurement is carried out by intention of knowing the comparison between the actual object and then the dimension of the map. The results scale the real object dimension. The tables show the result data in the comparison between object dimension in map. We get the ratio of the real object and the represent object in the map is 1 per 5.81. So the conclusion is this experimental research proved that wire-based SLAM 2 algorithm can be implemented to an AMR or autonomous mobile robot to perform SLAM, or we know SLAM is simultaneously localization and mapping, which is using a monocular camera as a sensor. The system is able to represent object in its environment into a map with ratio between map dimension and actual dimension of 1 per 5.81, where SLAM 2 algorithm implementation was managed to create a map and do localization. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Okay, thank you, Mr. Nur Jamiluddin. Perhaps because the time is very strict.
Yeah.
We must follow to second presenter, I think. Yeah. We can discuss this time. Okay, Mr. For second presenter is Maze mapping based modified depth first search algorithm simulator for agricultural environment, and I think will be presented by Mr. Justin Sunarto Budiman, I think.
Yeah.
Yes. Okay. Mr. Justin, the time is yours.
Okay. Thank you.
15 minutes maximum. Yeah.
Yeah.
Okay. Thank you.
Okay. Hello, ladies and gentlemen. My name is Justin Sunarto Budiman from Parahyangan Catholic University Indonesia. Now I am going to presenting about our research, maze mapping based modified depth first search algorithm simulator for agricultural environment. Introduction. The first is autonomous mobile robot has been widely used in various fields. The various field can be seen in figure 2. And recently, the autonomous mobile robot has been used for smart farming to carry out agricultural tasks such as seeding and harvesting and crop monitoring and inspection. And to be able to carry out its duties, the MR must have the ability to map the environment. The MR research on mapping is related around the maze solving robotics using the variety of algorithms, which is classified into 2 groups. The first group is the known maze environment algorithms, and the second group is the unknown maze environment algorithms. In order to test the proposed maze solver algorithms, a maze is physically built, and the mobile robot is programmed using the proposed approach. But by physically build the maze and the robot, we might there might be some risk. The first risk is to build a large maze, we need a large room availability and a large cost. And also the second risk is the maze and the robot will might be damaged when testing process due to mechanical and software error. Therefore, in order to test the algorithm without risk, in this research, we developed a Python-based simulator for simulation of sensor-based mobile robot for mapping an agricultural landscape. This landscape is considered from robot's point of view and considered as an unknown maze. So the plants will be representing by the wall. The description of our systems is the first, the robot has 4 heading direction, north, east, south, and west, and there is a set of priority moving roles while the robots move in the maze. In figure 4, the moving priority, the first one is move forward 1 cell. The second one is turn right, then move forward 1 cell. The third one is turn left, then move forward 1 cell. And the last is turn around, then move forward 1 cell. In figure 5, we give you an illustration about the robot movement with priority. There are 3 conditions with labels 1 until 3. The first condition is when the robot facing east. There are 2 available ways on the front and the right side of the robot. Therefore, the robot will follow the first priority to move forward. The second condition is the robot is facing east and the robot is located at the dead end cells. That means there is no other possible way, and the robot will follow its 4th priorities to turn around 180 degrees and moving forward 1 cell. And the third condition is when the robot facing north, there are 2 available ways on the left and the right side of the robot. And by following its second priority, the robot will turn right and move forward. For simulator purpose, the input of our systems are robot's heading, left, front, and right sensor signals, and XY coordinates of the robot's position. Also, we use 3 lists called visited list, depth list, and depth core for record keeping. The visited list stores the already visited cell coordinates, and the depth list stores cell coordinates that have more than 1 possible way, and the depth core stores unvisited cell coordinates. The flow diagram of the simulation, the first process is wall scanning to find all the possible way that the robot can take, and the second is print the scanned wall. In simulator, the wall represented by white blocks. The third process is check current coordinate on visited list. If this current coordinate is not present in visited list, the robot will record these coordinates and execute smooth subroutine. But if this current coordinate is present in visited list, the robot will check depth list. When the robot check depth list, if there are any coordinates recorded in depth list, the robot will execute depth case subroutine to move to the last coordinate recorded on depth list. But if there are no other coordinates recorded on depth list, the robot will execute go home subroutine. Next is the moving decision. The move subroutine decides the moving decision of the robot based off heading and sensor information. Table 1 represent all the possible combination of the sensor, which 0 represent the possible ways and 1 represent a wall. So in figure 6, we give you an example about how the sensor read the condition of the environment. In figure 6a, the decision is to move forward 1 cell and write the robot current coordinates to visited list because there is no other ways on the right or on the left of the robot. And from figure 6b, the decision is to move forward and write the robot current coordinate to visited list and write robot's right coordinate to depth list. Note that each coordinate in visited list and depth list has unique sequence number. And we use this sequence number in depth case subroutine. When the robots arrive at a junction, its unvisited list is recorded in the depth list. And we use 3 variables namely CF, CR, and CL, and used to represent the left, front, and right situation respectively. In figure 7, we give you an example about how CF, CR, and CL used. If there are no other way, no possible way on the right or on the left side of the robot, like figure 7a, the value of CL and CR will be nil, and the CF will be equals to val. Val in here equals to sequence number of unvisited list, unvisited cell, minus sequence number of the possible way in current robot position. By using a subtraction method, we determine the movement of the robot. The robot will move to the cell with the smallest value in the depth away list. The next is when the robot has visit all the cell in the maze, the robot will execute go home subroutine, which also use CF, CL, and CR variable, and the file value of this subroutine is 0, which represent the sequence number of initial location of the robot minus sequence number of the possible way in current robot position. In the subroutine, the robot will move to the cell with the biggest value in the go back list. For the simulation and analysis, we use the figure 9 maze as our maze and in this research. And before we start our simulation, we need to determine the robot heading and then the robot location. In figure 10, the robot heading is east and the robot location is minus 264, 264. The robot will continue moving on the maze by following its priority and also environment condition until the robot is located at coordinate minus 24, 224 in figure 11. In this condition, the robot found a junction at coordinate minus 72, 264, which is represented by point A, and the robot will record the right coordinate of the robot to the depth list and continue to move along the maze until it found a dead end cell. In figure 12, the robot have found a dead end cell and moved along by following its fourth priority to turn around 180 degrees and move back to coordinate that in depth list. Since the only coordinate on that list is point A, the robot will moving back to point A. And
excuse me, 4 minutes more.
Okay, question. And then the robot will continue to moving by turn left, and eventually the robot will arrive at point 72, 120 in figure 13. The only cell in figure 13 is point C. Then the robot must turn right and go to the point C as the last cell in the maze. After the robot arrives at point C, the robot will execute go home subroutine with the shortest path available in the maze. And in figure 14, the robot found the shortest path on the maze is C, B, A, and then initial position. Conclusion and future works. The simulator can visualize the robot maze mapping operation by showing the mapping results in the simulation area. And by using the DFS algorithm, all the cells in the maze can be mapped. However, the proposed simulator still has some limitation that will become our future works to overcome such limitation. And for hardware, we also considered a sensor that will be used. Typically, an ultrasonic sensor can sense a wall or obstacle. But since the vegetation is in an agricultural landscape may vary, we will investigate the appropriate sensor that accurately detects a wall or veggies in the agricultural environment as future works. We will also study the possibilities of using camera and image processing so that the turtle movement decision in the simulator area will be sent to the robot so that the robot movement will be the same as the turtle in simulator. That's all for me. Thank you.
Okay, thank you. For attendee, any question for these papers? I think it's very interesting. But I will give you to anyone have any question to Mr. Justin? Okay. Is there no question? I will continue to next presenter, Mr. Gede Haris Widyarta, I think.
Thank you so much, Mr. Ali.
Okay. The article, thank you for Mr. Justin. And we will continue to the third participant. The title is Control Lyapunov Barrier Function Implementation for Mobile Robot Model with Hardware in the Loop. So, Mr. Gede, the time is yours.
Okay.
Thank you.
Can I share screen?
Yes.
Okay.
Okay.
Okay. Can you see my screen?
Yeah.
Okay. Okay. Good afternoon, ladies and gentlemen. My name is Gede Haris Widyarta. I am a fresh graduate student from Telkom University, and today I will explain you about the research titled Control Lyapunov Barrier Function Implementation for Mobile Robot Model with Hardware in the Loop simulation. So, in this research, it consists of 4 authors. There are Gede Haris Widyarta, myself, and Mr. Muhammad Zaki Ramloni, and then Muhammad Ridho Rosa, and Mr. Bambang Rianto Trilaksono. So in this research, here's the table of content. First, we go to the introduction, and then literature review, then system design.
Sorry, Mr. Gede. Okay. I think the right part is blocked by some object, I think.
Okay, wait.
The right part of your presentation is blocked. Maybe some windows.
Is that clear?
Okay, it's okay.
Okay, I will continue. The last one is the conclusion. Okay, we go to the first one, introduction. So, mobile robots are one of the most widely used types of robot in industry. The main feature of the mobile robot, besides navigation, is the collision avoidance feature. So, to design a collision avoidance system, an appropriate control system is needed for the mobile robot. Based on these problems, a simulation of mobile robot model with a control method is essential to see the response of the mobile robot system. In this study, control method to be applied to the mobile robot is control Lyapunov barrier function, or we call CLBF. We use CLBF because CLBF has an advantage that it can reach the point of the stability in all initial stage and maintain system safety by avoiding barrier and reaching the destination point of the mobile robot. The primary reference for this research is the CLBF study in 2014 by Mr. Zaki and Mr. Bayu Jayawardana. So the researcher combined the method of the control Lyapunov function and control barrier function, which were then combined into control Lyapunov function. And then the result obtained are that applying the CLBF method in a closed loop system can reach a point of stability and ensure system safety by avoiding unsafe state through simulation. Here's the literature review. So in this research, we use one assumption for the mobile robot. In this study, the mobile robot model is assumed to be a system single integrator, where the mobile robot dynamics equation, or we call FX, is not used in the control system design. So the mobile robot dynamics equation will behave at 0 value, and GX, or the matrix input, is a second order identity matrix. The purpose of giving the assumption of single integrator system on the mobile robot model is to simplify the mobile robot model and produce an output in the form of position, which is the input for the CLBF. Then a closed loop system is formed as the figure I show you on the slide. So the mobile robot system with a single integrator system assumption has an input can be stated as U1, is the velocity of state x1 or the velocity of the horizontal axis x. Meanwhile, U2 is the velocity of the state x2 or the velocity on the vertical axis y. So, control Lyapunov Barry function. As I mentioned above, the CLBF method is one of the modern control methods initiated and developed in 2014, and the CLBF method combines two control methods, namely control Lyapunov function and control Barry function. The purpose of CLBF method is to obtain system stability and ensure system safety. CLF is symbolized by Px, CBF is symbolized by Bx, and CLBF represented by Wx. So CLBF equation can be represented as the equation I show you on the slide. Wx equal Vx plus lambda multiplied by Bx plus kappa. On the equation, Vx is the CLF equation, Bx is the CBF equation, lambda is the gain barrier parameter, where the higher value of the lambda is given, the more aggressive the system when avoiding the barrier. And the kappa is an additional control parameter. If the state is positive and kappa more than 0, then the system distance to the barrier will be closer, while when the kappa is less than 0, the system distance to the barrier is greater. In this study, CLBF also has an input in the form of mobile robot coordinate position in x and y axis and can be expressed as x1 is the mobile robot position in x-axis and x2 is the mobile robot position in y-axis. Okay, here's the hardware in the loop design. So hardware in the loop is a simulation method that use hardware and software with the aim that your simulation result produce values that are close to the actual test result in the actual environment. In this research, the design Hill simulation used the actual controller on the Arduino and a virtual fan on the Simulink. For data communication, we use the AKI or data acquisition device. So the step hardware in the loop, I divided into 4 steps. The first one is Arduino as an actual controller. We will send a control signal in the form of PWM or pulse width modulation. And then the control signal from the Arduino is converted into an analog signal with a DAC circuit or digital analog converter circuit. Then it's distributed to the AKI. And then the AKI controls the virtual plant on Simulink to run according to the control signal given by Arduino. And the last one, Simulink will provide a feedback signal to Arduino via the AKI. Then Arduino can process a new control signal. Okay, the next part is the system design. So we begin with the CLF equation. The CLF equation in this study can be expressed as Vx equal x1 square plus q multiplied by x1 and x2 plus x2 square. So this model is taken from the research in 2014, but we modified it by multiply the equation with q coefficient. So the q coefficient has a value of 0.001 until 0.1. The coefficient values is obtained from the result of trial and error experiments. So the closer the q coefficient to 0.1, the smoother the result. Then the CLF model is checked whether it has definite positive or negative, because to form a CLF equation, the value has to be definite positive. So from the CLF equation above, we take the 0.1 value for the q coefficient, then the derivative are obtained as LFV equals 0 because the dynamics for Fx is behave at 0, and then LGV is partially derivative from the CLF function to Gx, and Gx has a value for the identity matrix second order, so it has a value as you can see on the slide. And then we go to the CBF equation. The CBF equation in this study use the circular barrier equation because the barrier is in circle shape, so we use the circular barrier equation as represented by Bx, and M and N is the center of the point in the circle in the x and y coordinate. So the Lie derivative value for CBF is obtained as I mentioned in the slide. So LFB is once again is 0 because Fx is 0, and then LGB has a value because Gx is the second order identity matrix, and the value depends on M and N itself. So then after the CLF and CBF equation are solved, These equations are substituted into the CLBF equation. Then CLBF Lie derivative can be expressed as LFW is 0 and LGW is LGV plus lambda multiplied by LGD plus kappa. So here's the Hill experiment setup. I divided into 4 parts or 4 devices that I use. So the first one is PC. PC used to design and run the virtual plan through Simulink application. The second one is the AKI to start a communication between the virtual plan and the actual controller. And the third is the digital to analog converter, or we call the AC, to convert digital signal from the Arduino in the form of PWM to analog signal. And the last one is the Arduino Mega used as the actual controller for the virtual plan in the Simulink. Okay, here's the virtual plan. I explain it and describe into 4 parts. So the first block or the first part is the control signal receiving block from Arduino. And then the second block is a scope block that serves as a position and control signal data collector, then visualized into chart. And then the third is the single integrator system block, where the mobile robot is assumed to be a single integrator system. And the last block, block number 4, is the block for sending the output from the virtual plan to Arduino. Here's the system flow chart. On the left side is the virtual plan on Simulink flow chart, and the right side is the Arduino as the actual control flow chart. So we begin for the left side first. The first step to run the Hill simulation is to enter initial condition value. Then the virtual plan in Simulink is run. Simulink will receive a control signal from Arduino with the help of the AKI device, and then the virtual plan will process and produce output according to the received control signal. In addition, the virtual plan also sends output data to Arduino via the AKI device. If the simulation time runs for 4 seconds, the Hill system will give a stop scope command to visualize the output state and the distance data between the system and the barrier. So on the right side is the flowchart color. The initial stage initializing the system for declaring control parameter values, and then Arduino received the output state from the Simulink with the AKI. From the value received, the process of the CLBF method continues and produces control signal outputs, which are then sent to Simulink via Arduino PWM pin and the AKI device. Here's the result and discussion. Okay, on the table, you can see the control system specification that we use. First, we have the CLF equation with coefficient Q is 0.1, and then CBF equations. There are 2 CBF equations because we use 2 circular barriers, and then CLBF equation as I mentioned above. And then we got 3 control parameter. There are lambda valued by 2, kappa is -1, and gamma is 1. Gamma is the parameter to multiply the output. So 5 initial conditions were taken for simulation with MATLAB and the Hill system to test the virtual plan on Simulink. And to determining the control parameters value for the lambda, kappa, and gamma, the author used the trial and error method by looking at the effect parameter values on the Hill simulation result. Okay, here's the result. The right one is the simulation result, and the left one is the simulation result, and the right one is the hardware in the loop. As you can see, there are 2 barriers in circular shape. This one is this one, and 2 figures shows the result of the pathway plot taken by the mobile robot system model during the simulation and Hill with 5 different initial conditions. The 2 images both show the mobile robot system with the single integrator system assumption successfully avoids 2 existing barriers and goes to the origin or the destination point at 0.0. And from 5 initial conditions, we can take one of them. For example, we take the 3rd initial condition to see the control output and distance graph. Okay, here's the output. The right side is the distance to barrier graphs, and then the left side is the CLBF output. So the CLBF output I will explain first. The left side is the graph for the output control signal U1 and U2 from the field simulation. It can be seen that the time on 0.1 until 0.5 seconds, the system has significant value, increased value of this control signal because the system is approaching the barrier. Then when the time is on 1.5 seconds, the value of the system controls approach the stability point at 0. Also, in the figure on the left, the control signal generated by Hill has a noise caused by data transmission communication from Arduino to Simulink and vice versa. And then on the right side, there is a distance to barriers graph. So from the figure, we know the system avoids the barriers from the two graph because the distance often is not negative or less than 0. In the first barrier that shows on the blue line, the closest distance of the system is 0.069 meter. And in the second barrier, the closest distance is 0.49 meter. Thus, the system does not hit the barrier and can avoid it. So I conclude the system is safety is maintained. Okay, here's the data result summary. As you can see, the simulation result is better than Hill result. This is because in Hill we use actual controller, so there are many factors that influence the output system. Okay, conclusion. So the conclusion, the mobile robot dynamics is assumed as a single interrogator system. The proposed method shows the mobile robot can reach the origin and avoid the obstacles that verify the stability, proof, and its safety. The average percentage level of error resulting from the system testing with Hill is 3.89%, and closest distance to the barrier is 1.05 meter for the first barrier and 0.5 meter for the second barrier. And the future work, I hope Hill simulation will, with mobile robot, can use a complete mobile robot model, including dynamics and kinematics equation, as well as having dynamic barrier and the real implementation of a mobile robot assuming a single system integrator with child-based control can be realized in hardware form and tested in real environment. Okay, maybe that's all for me. Thank you.
Okay, thank you, Mr. Ketik. Any question from all attendees? Any question? Okay, well, I think I'm interested in your research. Why the result from simulation and from Hill is very different? The error average is 2%, I think.
Yeah.
Error average is different 2%.
Okay, thank you for the question. I will try to answer my best. So the difference between the result difference between simulation and Hill, I think it caused by so many factors such as data transmission, delay, and then because it transfer data in wireless way, so I think it's because the delay and data transmission.
Oh, okay, I see. The delay in data transmission, yeah.
Yeah.
Okay. And so maybe for processing time in Arduino.
Pardon me, sir?
Processing time in Arduino. Is there any factor?
Oh, yeah. Yeah, I think the processing time in Arduino is also influence the result because the code that I read is so long, and I think there is also influence the result of the system.
Okay. Yes, perhaps one day you can shorten your program, right?
Thank you, sir. Thank you for your advice.
Okay. Thank you for the presentation. And now we continue with the fourth paper. Title is Path Following Control of an Autonomous Bus Based on Lyapunov Stability Function by Nadana Aisyah Aziz from Bandung Institute of Technology. Okay, the time is yours, Nadana.
Okay, thank you, Mr. Ali, for your time and place. Let me share my screen.
Yes, of course.
Okay, can you see my screen, Mr.
Yes,
Ali?
yes, yes.
Okay,
Okay,
thank you. Thank you.
please.
Wait. Okay, Bismillahirrahmanirrahim. Hello, everyone. Okay, in this beautiful day, I would like to go for my, our presentation with title Path Flowing Control of an Autonomous Bus based on Lyapunov Stability Function. This is a research by me, Nadana Aisyah Aziz, and my fellow Joshua Friendly, Fahmi Rizaldi, under the supervision of Mr. Augie Widyotjatmo and Mr. Yuyunasi Nazarudin. We are from Instrumentation and Control Research Group, Institute Technology Bandung. So this research will introduce a method regarding the movement control of an autonomous bus through a path flowing algorithm, which is designed based on the error stabilization of position and orientation of the bus using Lyapunov stability method. Okay. This research is supported by Kemendikbudristek of Republic of Indonesia under Fundamental or Applied Research Team 2021 and in part by the research program of Institute Technology Bandung. And the outline of the presentation is shown as follows: that are introduction, and then deriving the path flowing control algorithm, then simulation and implementation results, and the last is conclusion. So we first move to the introduction. So over the past few years, public transportation has been a serious matter is to be solved in Indonesia. For instance, in Jakarta as the capital city of Indonesia. From the data from Indonesia Central Bureau of Statistics, the number of motorized vehicles in Jakarta has reached 80.6 million units. From the demographic, you can see in your screen, from all the registered motorized vehicles in Jakarta, only 2% is bus. Only 2% of it is bus or public transportation. So the result of the insufficient number of public transportation is severe congestion. So we get data that in average, people can spend about 55 hours move on the road per year only on the road. And then we can propose the solution is mass rapid transportation, which can mobilize a large number of people and reduce the space taken by the vehicle. And as we move to the autonomous system era, so we can direct to the autonomous bus to be the solution of this problem. As autonomous bus over efficiency, reduce environmental impact, cost saving, reducing congestion, and increase the reliability of the bus. And also, the autonomous bus will be used in the future in the capital city in Indonesia. So I think this research is important and aligned with governance program. So in this paper, we propose an alternative control method for forward-moving maneuver of autonomous bus, where the control objective is to align the head of the bus to the desired path. We will model and measure the kinematic error of the position and the orientation of the system. And also, the objective of the control is to achieve the origin of the error. And we use Lyapunov stability theorem. By using this, the origin can be characterized if it's stable, if it's asymptotically stable or unstable. So we also introduce an objective function to optimize the control parameters. Okay, Now we move to the path following control. First, we introduce the kinematic model of the forward-moving maneuver bus. So as you can see in the right side of the screen, this is the model of the bus. The system is a rigid body with length L, which is the difference distance between the front wheel and rear wheel. And this is also the reference point, the center point of the front wheel, expressed by variable h, and the theta here is the orientation of the system, which is the angle of the x-axis to the position vector p. Basically, the bus is controlled by two inputs which are the traction velocity v and steering angle alpha x. And we made two assumptions here that the rear wheel drive system is assumed to be differential wheel, and the second, the steering angle input is constrained between minus p by 6 and plus p by 6 due to its steering movement capability. And this is the kinematic model of the. Okay, after we deriving the kinematic model of the bus, here we derive the path following objective. So in deriving the controller function, we use Lyapunov stability testing to perform to observe, whether the system is stable or not after implementing the controller function. So if you see in the right side of your screen, this is the bus, the model of the bus, and this is the path P with a certain position and orientation. And we introduce also the error of position, which is the deviation of the reference point of the bus and the path, and the error of the orientation, which is the deviation between the orientation of the bus and deviation of the tangent of the P-line curve. Okay, after this we can, basically the definition of the stability and objective of this controller is to make the origin of the system asymptotically stable, or the error is zero. So we can derive the kinematic equation defined as below, and by the Lyapunov stability theorem, we can derive the first derivation of Lyapunov like this, as shown in equation 3. So if you see from the equation 3, you can see that the system is basically unstable at the equilibrium point, or in other words, the system will not be able to go to this condition in accordance to desired path. So to handle this, we also introduce steering control function that can make the error of the position and error of the orientation zero, or in other words, the first derivative of the Lyapunov function is greater than zero. So the variable steering angle alpha is defined as this, and if we substitute this steering angle to the derivative of Lyapunov in the previous slide, we can get this P dot as minus K times error of orientation square. You can see this, it contains K, with K can be any positive number, I think, okay, this means that the value of P dot is less than zero, or semi-definite. So, based on the Lyapunov stability theorem, the point of error of orientation can be asymptotically stable, because of when time is infinite, the value of error of orientation also goes to zero. And then we can see this is the steering angle contains K. So here we conduct optimization of K to find out how to obtain the optimal K with this objective function. So the objective function is to minimize the error of position and error of orientation. So we can see the most optimal system performance. And to get proof for error position to be zero as well, we can substitute the steering angle to the kinematic error, so that we can see this and as error of orientation is 0, so error of derivative derivative error of the position is also 0, and the position error value will go constant value, and error of the orientation is 0. Okay. Next, we also derive the traction velocity control function. This controlling traction velocity is needed to make the movement of the system not too aggressive, especially where the error of the system is too large. So this is the traction velocity control function. So after deriving all the algorithm, we will conduct the simulation and real-time implementation. The simulation and real-time implementation will be conducted in two types of parts. Okay, this is the first part. This is the first part. This is the straight line, and the second part is three segment lines that form an S shape as shown in this figure. The first part is function with desired position y 135 cm, and the orientation is 0 degree. And the position and orientation of the second part you can see in here. That the first segment is x is 240 centimeter with orientation of 90 degree, while the third segment has desired of y is 180 centimeter and orientation with theta 0 degree. Okay, so the real-time experimental investigation was also conducted in this research to verify the path control algorithm. We use miniature scale bus made from EV3 bricks. This is the picture of the miniature with some sensors around it. This resembles the real bus with length and width. With the miniature is 39 cm and 55.5 centimeter. So this is the experimental setup. All the sensor here, not MCU. Not MCU is on the top of the miniature bus. Is sent to the computer using MQTT protocol. And in the computer, we use MATLAB to build the algorithm, and we send back the input control or input law to the bus, to miniature bus to see MQTT as well. And then we move next to the right side here. This is the block diagram of the system. So basically, this is the desired position and design orientation, that point I mean, and this is the output. The position and the orientation of the bus is sent using indoor position system, and then it fed back to the path following controller. And here we also compare the output of the system with the set point. So it exhibits error or it produces error, and we use error to we use the error to produce the input law. Okay, after path following controller to the algorithm, then the input law is produced and it fed back to the actuator of the bus. And then the simulation and implementation also conducted with three themes. First is the first path simulation and real-time implementation with various of k value. Then the first path simulation and real implementation with various initial conditions. And the third is second path simulation and implementation with various value of k also. So we move next. This is the simulation and real implementation result. This is the first path simulation with variation of k. We use a variation of k that are 10, 20, 40, and 80 with initial conditions as follows. This is for the K10, this is for K20, K40, and the K80. As you can see, all the bus can go to the desired path, and if you can see more, it is intuitive that by increasing the K, the control became more aggressive. You can see it took longer for system in the K10 to follow the path or to be stable than the K of rather than K80. And also it can be classified for of the objective function that is shown in table here. As we increasing the value of K, the value of the objective function somehow becomes smaller, which is the system performance is increasing. So this is the first part simulation with variation of the initial condition. We have for initial conditions, I mean, to conduct this simulation, this is the first, second, and third, and fourth initial condition. You can see here, and this is the result. And you can see from the 4 initial condition of the system, the bus still can reach the point of equilibrium. I mean, they can follow the desired path, or they can be stabilized perfectly. So it can be proved, it can be said that it is proven that the system is asymptotically stable. And then this is first part real-time implementation. The left side is real-time implementation result with variation of K, and the right side is real-time implementation result with variation of system initial condition. We use K like before, K10, 20, 40, and 80 for the real-time implementation. So it can be observed.
Sorry, Nadana, your time is more 5 minutes more.
Okay. Thank you. So it can be seen that the controller can make the bus follow the path perfectly, and it also can be seen here. The objective function that as we increase the K, the objective function also be smaller, so the system is increasing. It also, you can see also in here the real-time implementation that in any initial condition, the system can go to the desired path perfectly. And this is the second part, simulation and implementation. The left side is the simulation, and the right side is the real-time implementation. For the simulation, we use variation of K 60, 70, 80, and 90. Meanwhile, in the real-time implementation, we only use K 80 and 60, as this K can bring the system to the path more faster. So you can see this that all result by simulation or real-time implementation, the proposed algorithm of the path following controller can bring the bus into the desired path perfectly. Okay, so we can conclude from all the implementation and simulation result that the proposed path following control can bring the autonomous bus system to follow the desired path. And by using the formulated steering control function, the bus system will always go to the desired path wherever it started with any possible initial condition, because the origin of the error is assured to be asymptotically stable. And also the objective function also plays a major role to determine the base K value for the controller that will affect the aggressiveness of the controller. Okay, these are references that we use in this research. Okay, thank you. That's all for my presentation. Then time and place, I give back to Mr. Ali. Thank you.
Oh, thank you, Nadana. Any question for Ms. Nadana? Very interesting, because Indonesia is still developing bus transportation.
Sorry, Dr. Ali, I have one question, if you allow me.
Okay, please, Muhammad Abu.
Yes, interesting topic. The question is about the experimental implementation.
Yeah.
Like your optimization depends on optimizing the error and the desired path and actual path. So how did you measure the error? What sensor did you use?
Okay, basically thank you. I'm sorry. Thank you for your questions. I will try my best to answer your question. So I think it is interesting that I see that this is we doesn't use any error indicator to see if it's great or not as the objective of our research is to follow the path perfectly. So I think it is one missing in our. I have to say that this is something missing from our research that we does not use any error indicator like RMSE or IAE like that uh, to present the error of the system. That's all that I can explain to you.
Okay. Is it answer the question?
Yeah, Mr. Mohammed, is it? I'm sorry if I can satisfy your question.
Thank you. Thank you.
Okay.
Okay. Now, thank you for Miss Nadana. And then we know continue with the fifth. Yeah.
Okay.
The
Thank
fifth.
you.
The fifth presentation. The title is Development of a Robotic Arm and N Effector for COVID-19 Testing by Mr. Muhammad Abu Al-Maluk from Hashemite University, Jordan. Okay, Mr. Muhammad, the time is yours.
Thank you. Just let me put the mic on.
First, let me share the screen. Okay. Thank you so much, and hi everybody. The subject I'm presenting today, it's about development of a robotic arm and end effector for COVID-19 swab testing. This work was done by Hazem, Fadi, Zaid, Michelle, and myself from the Mechatronics department in the Hashemite University in Jordan. I'd like to start the talk with this figure taken from the World Health Organization. This was taken on November 12, 2021. It shows that more than 250 million confirmed cases and more than 5 million confirmed death cases were reported by that date. And this is because of the coronavirus or the COVID-19 virus. So everybody knows that this virus hit us all hard in almost all aspects of our life. And the way we are conducting this conference is just an example of that. It's having it to be virtual because of this virus. So I think everybody knows that COVID-19 is diagnosed using what is called the PCR test. This test is usually conducted manually by healthcare workers. The problem is that this manual methods bring the health workers in close contact with either infected or suspicious to be infected persons. Sorry. So, we know that the healthcare and co-op workers play the most important role in fighting the COVID-19. So we need to protect them as much as possible. And we know all that there are protocols, equipment, and protecting tools available to do so. And we as an engineer, we need to do our part So one of the way to try to protect the health workers is to investigate implementing robots in fighting COVID-19. Now, this figure here has been taken from the IEEE Robotics and Automation magazine recently in March 2021. It shows some of the main areas where robots can be implemented. First, we can implement them in prevention, like UV disinfection, in screening, like in vital sign monitoring, diagnosis, like in swabbing. This robot here is taking a swab from this person here, or in treatment, where sometimes if the patient gets very sick, we need to put a tube to make him or her breathe better. So some people investigate using robots in intubation systems. The topic of this paper belongs to this category, the diagnosis, and more specifically, the swabbing type. I just want to go quickly through a couple of slides to review some literature, other researchers who did similar work. In this recent published work in 2021, soft pneumatically actuated robot consists of a conical shaped end oropharyngeal swabbing. So oropharyngeal means swab through the mouth or from the throat. So this is an example of some of the recent work on this topic. Another example is this 9 degree of freedom redundant rigid flexible coupling robot. Again, this robot conducts the swabbing through the mouth. And the last one I want to show you, it's again a recent work in January 2020, which means nasal means it's through the nasal cavity through the nose. Now, quickly, I need to talk about the two types of swabbing methods that are adopted globally. So there are two types. A, shown in the figure on the left, it's the throat oropharyngeal. It's through the mouth. And B, it's the nasal or nasopharyngeal swabbing. It's through the nose. Now, which one is better? At least in our work, we decide to go with the second type, the nasopharyngeal swabbing, which is through the nose, for two main reasons. First, literature shows that this method provide higher viral load, which means it will most likely gives better or accurate results. The second reason, in Jordan Ministry of Health, this is the adopted swabbing method. So this is why we choose to implement the swabbing the way it is. Now, I just want to talk briefly about the COVID-19 specimen collection that is adopted by Center of Disease Control, CDC. They have a long report that, but I just want to highlight 2 points. First, they recommend that the patient head should be tilted back 70 degrees when collecting the nasopharyngeal specimen. So the patient head should be at 70 degrees angle. And this is to enable the doctor to insert to be parallel to this, what is called the plantain bone, this bone. Doing so is important because the nasal cavity has tissues that are very delicate, and we don't want to damage or hurt the tissue in this area. They are very sensitive. So what happened is that when the co-worker insert the swab and to have it parallel to the plantain bone, it goes inside until it reaches this area called nasopharynx. This is a very sensitive area. The doctor should be very careful not to hit this area hard because it's very sensitive and it's very close to the brain. So then what happens is the doctor rotates the swab and retract it. So this is how it's done manually. Now, let's start with our proposed robotic system. So based on the CDC report I just mentioned before, we decide to build a head holder. The figure on the left, or figure here, the figure shown on this side, this shows the solid model of the head holder we designed. And we decide to go with designing a manipulator with a 3 degree of freedom articulated robot, and also to design a custom 2 degree of freedom end effector. So both models were built as we shown this figure on solid model, and we use the 3D printing technology to convert the design to the real robot you see on the right side. So this is the 3 degrees of freedom. This is joint 1, 2, 3, and this is where we have the end effector, the 2 degree of freedom end effector, which basically consists of prismatic and revolute joint. And this is the head holder, and this is HASM, one of the group. This figure here, I can talk, it shows the end effector in much more detail. This is the end effector here, and it consists of this is the prismatic joint, and we have a screw motor that allows this part to slide on this blue rail. And this is the revolute joint, which rotates the swab clockwise or counterclockwise. Now, it is very important to control the contact force between the swab tip and the human nasal tissue, because as I said, this tissue at the end of the nasal cavity is very sensitive, and you don't want to hit it hard. So we decide to put a fence, as shown in the figure. It's just 1 degree of freedom strain gauge. So this force sensor or strain gauge, it's only measures the force along this direction, the normal direction. The proposed robotic system is basically an active sensing and control of the contact force. And this is very essential. Let me go back a couple of slides here. Yes. If we need to, like, let's put it this way, humans have different distance for the nasal cavity. Like, we don't share the same distance here. It's different from one person to another. So we can't use a position control, because any slight difference or error in positioning will hit this area and may damage it. So we need to have a force control while the swab inside the nasal cavity. So that's why we decide to have the active sensing and control force control. Based on literature, they reported that a range of force between 0.35 Newton and 0.68 Newton were suitable, and it will not cause congestion or injury to that sensitive area. So we conducted some preliminary experimental tests. What you see here on your left side is a real size head phantom model. We have it in the medical school in the university. It's a medical model that the nasal cavity in this model is similar to the real cavity in a human. So we conducted some tests on this phantom model, and what we see here on the right side, this is the normal contact force response during the swab sampling test. So first thing to note is that the whole test took like less than a minute, about 50 seconds to conduct the whole test. And the test is divided to 3 stages. Let's start at time 0 here. Time 0, the manipulator moves the swab, and this is done manually by an operator who is far away from the patient and control the robot remotely. So first, the operator moves the swab and bring it close to the opening of the nose with the angle, as I mentioned, the 70 degrees angle, which this head holder help us to get. And then it comes the end effector rule, where it starts inserting the swab. And here we see that the force increases until it has this peak, which is about 0.6 Newton. which represent that the swab reach the final destination. It can't go further. And with the active controller, we managed to control the impact force or the contact force not to exceed the 0.60 Newton, which is safe according to the literature. Then during this region here, we have the collecting the viral, like the swab is rotating clockwise and counterclockwise. And the last stage where we have the swab retracting, that we remove the swab out of the nasal cavity. So we conclude that the normal contact force was successfully controlled and maintained below 0.68 Newton, which were reported in literature to be a safe and comfortable amount of force to conduct this test. Finally, conclusions and future work. A robotic system for COVID-19 nasopharyngeal swab sampling was designed and built. This robotic system consists of a 3-degree of freedom arm, 2-degree of freedom effector with force sensor. The robot is controlled remotely and from a safe distance. The preliminary results we conducted on the real-size head phantom model show that we were able to maintain and control the contact force below 0.68 Newton, which is essential in protecting the interior tissue of the nasal cavity from any injury. Now, future work, we know that we still have long road to go through. We're thinking of conducting further quantitative studies, probably on human volunteers. Also, we need to improve the position and force control, accuracy, comfortability, and also we need to see, like this robot, what is the success rate of PCR test, like put it on a real test and see how good is the sample we obtained. Well, that's all I have. Thank you, and I'll try to answer your questions.
Okay, thank you, Sir Muhammad Abdul Al-Maluk. Okay, any question from participants?
Hello, Mr. Ali. I have one question.
Okay, please, Mr. Justin.
Hello. Okay, thank you. Hello, Mr. Muhammad. I just curious about what is the reason why do you not use camera in your NF vector? Because similar research mostly using camera for positioning their NF vector. Why do you not use camera? Thank you.
Okay. The camera would be like if the person is far away, you're right. If I think if the person operating the robot will be far away and can't see exactly where this swab is going, yes, we need a camera. Definitely we need a camera. Like, but currently we are just in the first stages. Like we didn't test the system on COVID-19 patients, so we still can see where the swab is going. But you are right. Once we have the vision, we can't see where the swab is going. Yes, we need a camera. Exactly.
Okay, thank you, Mr. Muhammad.
Okay. Okay, thank you. And any else from participants? Okay. The time is okay. Now, thank you for Mr. Muhammad Abu Melu. Thank you for your presentation. And now we continue with the last presenter, Mr. The title is Kinematic Design of Integrated Rotational Axis Mechanism for IGUS Delta Robot from by Mr. Leonard Rusley. Okay, Mr. Leonard Trusley, time is yours.
Thank you. Thank you all for the opportunity for me to present this at this conference. And I would like to share a little bit from our projects on kinematic design for Delta robot. Okay, I'm sorry. Okay, is the full screen showing?
Yes.
Okay, great. I think I would like to. Okay. So let me introduce the project before we start. The project was a cooperation between IGUS, Beckhoff, and Swiss German University. This is the first stage of the project at IGUS booth in the manufacturing trade show in 2019. It's a 3-axis Delta robot. They sell bushings for machines, and because there is a need for the controls, they only sell the mechanical frame and the mechanism for the Delta robot. There is a need for the electrical actuator and also the control software. That's why we form a cooperation between SGU, Beckhoff, and IGUS. The actuators is supplied by Beckhoff, and the control software is supplied by SGU. Now, after the development of this Delta robot that is complete and able to be commercialized, there is a need for the additional rotational axis. And this is where we develop the project for a further development. The Delta robot, as you know, has 3 degrees of freedom that is incapable of rotational axis during the pick and place. And its superior speed makes them a choice for, whenever you need speed, people use Delta robot for pick and place. Unfortunately, you can only move from A to B and not be able to rotate the parts. Now, for some applications, that is a limitation. And so the project here is to add a rotational axis to the 3 translation axis of the Delta robot. So we are able to rotate the object during the pick and place motion. This shows the working envelope of the IGUS Delta robot that we developed before in the phase 1 of the project. And we want to maintain this working envelope, and whatever rotational axis that we add to this Delta robot should also be able to reach to the ends of the working envelope. Now, I mentioned before that the end effector of a Delta robot is very light compared to a arm robot. For example, here, you see that the arm robot has actuators at each joint of the arm robot and making them very heavy in terms of its inertia. The Delta robot is not. The end effector of a Delta robot is very light. It's only at the end here, and the arms tends to be very light. So again, whatever we add to it, not the end effector. For example, this to do is just add a stepper motor or a servo at the end effector. That will be the natural solution. But however, adding a motor at the end effector will defeat the advantages of a Delta robot. So we will add a kinematic linkage such that the servo for the rotational axis can be maintained away from the end effector, but also connected to the end effector via some kinematic linkage. So that is really the goal of the project. We came up with some design concepts, mounting the motor here and having a telescoping axis here, but the telescoping axis will add too much inaccuracy by having multiple pin in a slot joint. We also consider mounting the servo way up top, and then having 2 pin in a slot joint, having a sliding joint on the middle frame here, and having 2 universal joint. However, this also have too many degrees of freedom that will create some indeterminate positions. Therefore, what we came up with finally is a telescoping double universal joints. A single joint of universal joint is like this, but it does have a fluctuation in terms of the angular velocity. The double U joint will provide a constant velocity as long as we maintain the input and the output shaft on the same virtual plane. However, to maintain the working envelope, we also need a telescopic motion. So in summary, we came up with a double U joint with a telescoping member in the middle. So something like this. However, we will accomplish this using a slightly different geometry. So the one U joint on the top here near the motor, another universal joint near the gripper, and a sliding middle member as a telescoping member. Like I mentioned, the universal joint will have a speed change at the bend angle of like 45 degrees. The fluctuation is very, very significant, which makes it subject to vibration and all kinds of problems. And so by having a double U joint, this will remove the speed fluctuation. As for the motor selection, well, we made some assumptions in order to size the motor. We assume we will need a cycle time of 0.2 seconds for one rotation, rotating the end effector, an acceleration and deceleration of 35 milliseconds. So there is a ramp up and there is a ramp down. This just further improve the reliability and also longevity of the joints. So we do want acceleration and deceleration rather than an abrupt start and stop. This will come out to be 380 RPM at the maximum or constant velocity. Taking into account the moving mass moment of inertia, using our solid modeling software, we can calculate the mass moment of inertia. It comes down to 2 times 10 to the minus 3 kilogram meter square. This acceleration, which is 196.4 radians per second square. Therefore, the torque for the acceleration and deceleration needed, assuming no friction, because they are insignificant compared to the acceleration and deceleration, the required torque for the servo will be 0.4 Newton meters. The motor selected then is the Beckhoff AM8111, which delivers a 0.16 Newton meters of torque, which is plenty adequate for our needs. Here are some of the motor mounting and coupler. We use all EGUS bushing because obviously we're doing this for EGUS product. Therefore, any spare parts preferably will be an EGUS product. They are plastic bushings that are self-lubricating, maintenance-free bushings. And so serves our product very well. Here is an example of the pin in the slot sliding joint for the telescoping member. Here's the top motor mount and the bottom motor mount. We make this to clamp to the existing structure, so we do not make like drill any holes or make any permanent modification to the existing frames for now. In order to save space, we have to make the T joint, the T member of the universal joint in such a way so it saves us space. A design of the solenoid gripper is also made such that it is very compact, and we are able to just use a very simple solenoid with a very short stroke. The mechanism shown here that we designed allows us to have an additional, we redirect the gripping force from the linear stroke vertical into the horizontal motion, and therefore creating a gripping action. It is located at the end effector here. So after the implementation and fabrication, we we have done a reach capability test. The first one is on the extreme top of the working envelope. The second one is at the extreme low point of the working envelope. And so you see that the pin in the slot the telescoping member will extend to its maximum length. Here it is at a minimum length. And also we need to test the maximum side boundaries of the working envelope. And here the telescoping member is also almost at the maximum, but not as far as the one reaching to the bottom of the working envelope. And so here are some sample pictures of the actual implementation. Here is at the top, here is at the bottom, and here is at the extreme edge of the working envelope. Again, this is using existing back-off servo motors. And this one is a preliminary model using a stepper motor, but in the actual implementation, we use back-off AM8111. We did also some tests for the positioning error. Here is an example of a step input. Notice that the time is pretty short. So this ramp up is not that slow, really. I mean, we're talking about 1/10 of a second here. And there is an overshoot, a slight overshoot of the controls because it is not yet tuned. The closed loop parameters are not yet optimized at the time of writing of this paper. So we see there is some overshoot and then it settles down into the target set point. There is some inaccuracy due to the pin in the slot joint, the telescopic member. They are about 0.2 degrees, I believe. And hold on, let me look it up again, just to make sure I got this right. It is 0.1 millimeter dimensional tolerance on the 3D printer. And therefore, this translates to about 0.5 degree in the rotational axis. Now, we do have 3 points where this can introduce an inaccurate position and introduce a backlash to the kinematic linkage. One at the top U-joint, one at the telescoping member, and another one at the bottom universal joint. The backlash being measured by the servo here is about negative 0.5 degrees to about 0.6 degrees on the forward motion. And then going from 90 degree to 0 degree, we see also a hysteresis or a backlash going on here. Now this will be further, obviously much better once we get to an aluminum pieces and metal CNC machine members of the linkages rather than a 3D printer. So we believe a combination of the PID tuning of the servo as well as some better machine kinematic linkage will reduce this error very significantly. Let me play the video demo of the implementation of this rotational axis. So it is called fourth axis, basically it's the rotational axis. So we programmed the demonstration to test the outermost position, rotate, and also do a test run on the back of PLC controllers. So picking and place at different points here. And also we will have another test with the gripper rotating. So this is a package for a demonstration in the manufacturing trade show that we usually have every December or every November. And they're actually commercializing this as we go. Hopefully it will enhance the features being offered by the Delta robot. That is all from me. Thank you for your time, and I hope we shared some useful information.
Okay, thank you, Mr. Leonard. Any question from audience? Okay, there's no question anymore. Thank you, Mr. Leonard, for your
Thank you.
interesting presentation. And now, as our last, Mr. Muhammad Abul, please.
Thank you. Very, very interesting topic. Just want to make sure I understand. You added that telescope joint, which is a passive joint.
Yes.
Okay. It's there is no fluid. It's not a hydraulic. It's not pneumatic. It's just
No. It adjusts as the 3 axis of the Delta robot moves. It will stretch it, and it will basically follow through with any motion from the original 3 axis.
And it didn't affect the workspace at all. Like the workspace stays the same as original.
Yes, that was the challenge. We have to come up with a geometry that will accommodate the same workspace.
I just wanna why didn't you think of using a spherical joint? Like, what's the problem with spherical joints instead of the universal joint?
We can also do spherical joints. It's not as simple to implement, but yes, that is definitely possible.
Because if it's a passive joint, well, you don't need to control it. It's gonna give you more degree of freedom. So
right.
But it might not be strong enough as
we can do a constant velocity joint, but there is a torque being transferred from the servo controlling the rotation. So there is no translational. The translation it's passive, but rotationally it's active.
Yes. Sorry. Yeah, you're right. Okay, thank you.
But constant velocity joint is also an alternative, but it's just a bit more complex in its geometry.
Thanks.
Yeah, thank you.
So, okay. Thank you, Mr. Muhammad Abu Maluk. Also, thank you for Mr. Leonard Priestley. And now, our audience, as our last presenter has concluded this presentation, I would like to give appreciation for all presenters and all attendees here. Thank you for the insightful presentation and discussions. I also apologize if there is mistake in name pronunciation. Also, we will send presentation certificate to by email for each presenter. And see you next time in the next morse conference next year. Thank you, and we close this session. Thank you.
Thank you so much.
Thank you. Waalaikumsalam.